International A-level students, for the Cambridge board, we have a free learning hub. You should go over here and get all the free resources that go with the lectures on YouTube, or you can just watch the lectures here. So make sure to click into each topic where you can find a selection of slides that go through all the units, slides like on the lectures. We have then short notes here for revision. We've also got lots of vocabulary sheets here for each unit and lots of comprehension short questions that are meant to be answered as you're watching the video. On top of that, we'll be releasing tips for the exam and lots of new lectures in the upcoming months. So make sure to register and also make sure that you're actually going to receive emails about updates on the course. So get on over there to the Learning Hub and enjoy some free resources. Hi everyone, this is Brian. If you're really enjoying these videos and they're useful, please do like them, leave some positive comments, and make sure you subscribe. By doing that, I can keep making these videos and helping more and more students. Thanks very much. Unit 1 for Cambridge International A-Level, Hydrology, River Processes and Hazards. This unit, we're going to go through three sections. We've got the drainage basin system, river channel processes and landforms, and river flood hazards and impacts. For each section, then you have a vocabulary sheet, short questions, revision notes, and these slides to download on the Geography Academy. So for the first stage, the drainage basin system, we're going to define the key components of a drainage basin, including inputs, processes, stores, and transfers. Explain how water moves through the hydrological cycle and the drainage basin system, and we're going to analyze the factors that influence river discharge and storm hydrographs. So let's begin. When we're looking at water distribution on the planet, about 97% is in the oceans as salt water. So of the remaining 3% of fresh water, it's divided into frozen water, groundwater, and surface water. So quite a high percentage is in frozen ice. We can see this in the polar regions, in the high mountains, in glaciers, and ice sheets. A very large 22% is still in groundwater, something that we focus on quite a lot in this unit, and then we can see 1% in the surface water. Then there's transfers and flows between those stores in the atmosphere. When we're looking at this area, we're going to focus on drainage basins. This is this area of land where precipitation is going to fall and it's going to roll down into one drainage basin system. So for example, if it rains here, it's going to flow into this river and that's going to join up with this river and that's going to flow out until it reaches the end. Likewise, if it rained in this valley over here, the rain would go into this drainage basin and would drain off into this area. So we measure the stores and the flows and how water moves in this area. And just to get familiar with this terminology again, we look at a watershed. So that's an area, a ridge that separates water flowing in different basins. So again, if it was to rain and the water was to land on this side, it might go into a completely different drainage basin that flows out that way than if the rain fell on this side and flows down here and to an estuary out that direction. Tributaries are where two rivers meet, and then the confluence is the area in which it meets, but the tributary is the smaller river that comes into the bigger one. So, for example, this is a tributary to the main river channel here. Okay, now we're looking at the river source. This is where the river begins. It's going to be at a high point in what we call the upper course, and it's going to flow down. As it's flowing down, then it actually gets larger in volume, and we'll have a look at that quite soon. The river mouth, or the estuary, where the river ends and reaches a body of water like a sea or an ocean or a lake into those regions. So just take a second, make sure you can recap, you understand each of these. So we have the sources. Here we have the Amazon drainage basin, so quite a well-known one, and biggest in volume in the world. And we can see all these sources in all these different areas create these rivers. Those rivers move down as tributaries to the main river and they join at confluences. And as they do so, the river gets larger and larger. The Amazon then is the yellow part here is marking the watershed, the area where one drainage basin goes one direction and the other goes the other direction. So we can see rivers that are outside of this drainage basin here who have their own drainage basin system. All right, for this section now, we're going to look at the stores and flows. It's really important that you at least have one visual that you use quite often. You might use something completely different than this, but it's just a nice one to come back to so you can mentally see all the main vocabulary. So we're just going to go through this section then little by little. We start off by looking at precipitation. So we can get rain, snow, sleet, hail. We can also get dew, for example, it can form as well. So there's many different types of precipitation. The one to think about a little bit is snow, for example, because snow will fall as ice crystals and then they will melt eventually. So there's a bit of a delayed response in the drainage basin for those. Same can actually happen with sleet and hail as well. So those would be inputs into the system. That's how water gets into the drainage basin. Now we can have a look at how it may come out of the drainage basin and looking at a few other processes. Evaporation, then, when the water turns from a liquid to a vapor and is lost to the atmosphere. Transpiration is where it's lost vapor from the stomata of plants into the atmosphere. So, in the tree itself, the water has to begin at the bottom by the roots that are down here, and it has to travel up through the roots, up through the tree, and then it leaves through the leaf and the stomata, which allows it to go into the atmosphere. Evapotranspiration then is a combination of the two together, so the total amount of water that goes back up into the atmosphere. Condensation is worth having as a definition. It's the water vapor into liquid droplets, so that's happening up in the atmosphere. So we can see here in the diagram now we are looking at a image that's showing a model of a drainage basin. We can see tributaries and we can see condensation, transpiration, evaporation happening. Precipitation is bringing the water into the system, and then a lot of it is leaving via the channel. So we can also see that some of this is going to go into the ground, infiltration, groundwater flows, and the likes, and it might come back out then again. So we're looking at the water cycle here in one small example in one particular drainage basin. Okay, so far we've looked at the inputs and we've also looked at the outputs. Transpiration, evaporation together, evapotranspiration. Precipitation then is going into the system. We also just mentioned that water can leave the system through river runoff, the discharge from the river in the drainage basin. So make sure you're familiar with all these words. Stop after each stage, answer any of the short questions, and also have a look at your vocabulary sheet to stay on top of things. Interception, then we're looking at trees, plants, the leaves. They're going to stop the precipitation from coming down. So the water droplets are going to land here. And at that moment, they can potentially evaporate directly off the plant. Or we could see through fall, where it's going to go through the little gaps here, just when you feel those big plops of water when it's been raining and you're walking under a tree. The stem flow then is when it travels down the stem, down the bark of the tree, and down to the base of the plant. So here we can have interception, and interception can go towards evaporation, or as through fall and stem flow, it can reach the surface. Next is what happens on the surface. Infiltration is the water entering the soil on the ground surface. We have impermeable and permeable surfaces. So with permeable surfaces, it will be able to get soaked in and absorbed into the surface there. Impermeable surface, like the rock here, the water may rain and flow directly off. So in some cases, like the rocks, there's going to be a certain level of permeability, but in general, then it might be a lot more impermeable than, let's say, soil. So here we have surface storage. Infiltration may happen, especially with different levels of permeability. If it doesn't, it's going to go as surface runoff, or it may also undergo evaporation at this stage. So this is the directions it can go with surface storage. When it enters in through infiltration, there's two ways it can go. It can continue to drop vertically down and move through the pores and rocks or the gaps that are in there, and it can make its way down into the groundwater storage, or it can go along the same angle as the hillside here as through flow. So notice the through flow is up here in what is marked as a soil section. So through flow flows through the soil in the downwards direction towards the stream. Also, surface runoff is doing the same thing. So both are running there. The surface runoff is on top, the through flow is in the soil. Now, when we get down to that stage, we can see that both surface runoff and through flow here that's in the soil water store is going to flow towards the channel. The channel in this case being the actual river. Now, the soil water storage can also go through a process of evaporation directly, or it can be taken up by the vegetation storage, where then it can finally go through the transpiration process. So those are the potential directions if the water doesn't move through the soil. Now, this is just assuming that the soil water store is able to actually take the water in. Sometimes it might be full, for example, and it might send the water as surface runoff. In the ground, then, we have a groundwater storage. And as we said at the beginning of this lesson, that about 22% of all water, fresh water in the world is locked up in aquifers, which are in the groundwater. So the groundwater flow is moving through the rocks, through the pores and the cracks and the joints. So we can imagine the speed it might take to move through these rocks. We can just see a side profile because this is open. Also, we can see entire lakes inside of cave systems here. Now, this is not what all of the groundwater looks like. Oftentimes, then it is within the cracks and the joints of the rock, and we have different levels. So, when infiltration happens and percolation occurs, this causes the groundwater storage to become full. So, in the area which is saturated with water, meaning that it doesn't have any air, it's just the rock and the water. This is where we will have our saturation zone, and this is where we will have our water table, marking the beginning of this. So the unsaturated area, or the vadose zone, then, where you can get air and water. Now, this area is definitely very important. If we think about it, for instance, if it wasn't to rain for a while, so there was no precipitation suddenly, and we were to get no surface runoff for a while, and it's also going to reduce the amount of through flow we're getting. So let's say both of those sources for the river's water deplete. So they can change very quickly based on precipitation. However, water moves slowest through the groundwater flow, usually. And this means that it's going to be more consistent. Evaporation isn't going to impact it very immediately. And we also know that, it's going to take a while for precipitation, for water to go down and add to the groundwater table. So even though the water level might go down seasonally, like let's say if there's a drought, you might see that the river doesn't go down to absolutely nothing. And this is why the groundwater flow is still providing water into the rivers or the streams. So this is something that can change as well, and something we have to monitor very closely. So we already mentioned surface runoff, also known as overland flow. There's different types that we will go into in more detail. So when we're looking at the channel, we're looking at the main river. We have the channel storage, which is overall the water in the system, the channel flow, which is the water flowing through the river, and river runoff. That is where the water reaches its estuary and then flows in there, removing the water from the water cycle and the drainage basin. So we've gone through all of these words, become very, very familiar with them. In physical geography, it's so important to be on top of all your vocabulary. Go to your vocabulary sheet in the Geography Academy, download it, make some vocabulary worksheets or any type of flashcards with those definitions, and make sure you can talk about this system very fluidly. If you do this, it means that you'll be able to write less in a more concise way and be very accurate with the rest of this course. Okay, part of this is then to just have a look at the hydrological water balance and its applications. So when we think about it, the balance we're looking at is very simple. Precipitation, and then we're going to take away the amount of runoff that leaves the system and the evaporation that leaves the system. And that's what we're left with then in terms of our water balance. So we want to figure out what's happening. Has the evapotranspiration rates gone up recently, and have the precipitation rates gone down recently? Well, if so, we're probably losing more than we're gaining in this drainage basin. So this is useful then for water management, making sure there's enough for seasonal change, or looking at things like industries like agriculture. Risk forecasting as well. It's very important to look at flood risk and to understand the dangers that are there, and look at the environmental damages and changes over multiple years, and focusing on things like climate change there. Okay, now we have to look into all the factors that influence the stores, the flows inside the drainage basin, to be able to talk about them very clearly, very accurately. We'll start off with porosity. So, looking at the percentage of the soil or rock made up of pore space, and permeability, the ability for water to connect and go through the pores. With clay soils over here on this side, we can see that there's lots of smaller pieces of clay that are together. It means that they have many, many pores. So if you were to count them all up, there would be a lot more than over here, where there's only a few large ones. So this means that they have high amounts of pores, but they have low permeability. And this is because, as we can see, the water can't move between the pores very accurately. So it's restricted there, meaning that there's some water logging at the top and there's not much water down below. So we can often see in this situation that if it was to rain, for example, not that much new water will be able to be absorbed by clay that quickly, which may lead it to cause things like surface runoff. So this is a case where the soil water store just might not be able to infiltrate that much, and it will send the water in the other options, which is either to be evaporated or go as surface runoff. So this can happen in clay, whereas sand works in the opposite way. It has a low amount of pores, but it is able to permeate through and move through those pores very easily. This would mean that the top then is not very well provided with water, and that a lot of it drains off. So large pores, water drains quickly. Silt is somewhere in between, where it can hold water at different levels and then allows it to also move through there. So sand, large pores, high permeability, rapid drainage, low water retention. Silt, intermediate pore size and permeability, easily compacted and surface sealed. Microscopic pores, potentially high porosity, low permeability, and slow drainage and high water retention for clays. Now, this is important because you are expected to write using examples, so having named types of soil is going to help you a lot in explaining all the different features. In most soil water storage areas, then it has a field capacity. What is the ideal amount of soil for growth in that region? In its drainage, we would see that sometimes it could take days or it could take a few hours for water to pass through. And pore size, obviously, as we mentioned, is very important as well. We're going to come back to this idea about annual change quite soon. When we looked at surface runoff, I mentioned that there could be a few different types that we have to know about. Hortonian flow is where the soil tries to absorb the water. Infiltration is trying to occur, but the excess water begins to flow over the surface, leading to surface runoff. So therefore, the precipitation rate is greater than the infiltration rate. In this area here, we can see it happens quite a lot in urban regions or dry soils, for instance. The saturation excess flow, then looking at soil pore spaces filled in addition to rainfall, cannot infiltrate. So we see this in compact surfaces, mainly in urban spaces. With the antecedent soil moisture, this is looking at the idea that it may have already absorbed quite a lot of the moisture and has saturated completely. So we can see the way that clay has a lot of water in it. If it was to rain today, and we'd see it filling up with water, and then it was to rain tomorrow, we are leaving the chance of surface runoff then much, much higher than it would have been before. Okay, now before going into this section in detail, it's also worth talking about the geology. This comes into it in terms of permeability, but also just in general, it's good to know the foundation of most rock types. As most of you will be studying this unit, first I'm just going to spend a few minutes just discussing different types of rocks. The first one is the igneous rock. When magma cools down very suddenly, this creates then different types of igneous rocks like granites and basalt, depending on how they formed. These are particularly what we would call hard or resistant rock. They have a very low porosity because during the cooling process, this meant that a lot of their crystals then were tightly packed and interlocked, reducing the amount of space that water has to pass through it. This means its porosity is very low and it has a low permeability. So water cannot pass through there as much. So exposed rock without any soil on the top, we would see a lot of surface runoff. Here we can see sedimentary rocks, and again, they're kind of exposed. They're not covered in soil in this case. Sedimentary rocks then are formed over time. There's accumulation, compaction. So if we imagine this was at the bottom of the sea at one time, and all of the deposition and grains got stuck at the bottom of the sea, and over time, more layers were added and more layers were added. And then it just compresses under its own weight under time. This is why we can actually physically see the lines here, for instance. So this is sandstone that's made up of grains of sand, very rough, coarse to feel. This one in particular then is going to be quite porous. So it allows for water to permeate through it. So if we have this as our groundwater level, we could see that water could percolate through it much faster. Okay, so when we have a sedimentary rock forming, we can also see that it might get buried over time. Also, igneous rocks may get buried over time as well and go back into the ground. And through heat and pressure, they can become metamorphic rocks, meaning that the rocks change into something new, a new characteristic. So limestone is a sedimentary rock, just like sandstone, and it's very prone to changes due to weather. But if it gets buried, then it can become marble and be slightly less permeable. So this has a low porosity because of the pressure. It squeezes everything together, heats it up, and changes the composition. So low permeability and low porosity for that one. In terms of permeability, then, primary permeability is passing through the pores like sandstone. We can now see how grainy this one is. Secondary permeability is the ability to go through fissures, joints and fissures like we can see here. So if we can imagine this happening even where we can't see it underneath the rock, we have all these fissures that water can flow through, more so connected with carnivorous limestone. It's a type of rock that will come up again and again in the course. Good to get used to it and to start writing about it and using it as an example. Here are a couple of examples of the rock types over. So just as a further example of that, we have chalk here, a porous sedimentary limestone, primary porosity, and can store a lot of groundwater. So it is increased by also having joints, cracks, fissures all around in different areas in which water can pass through easier, but also is high in porosity. So just stop for a second just to double check you're following this, everything seems okay. Just pause it and think to yourself, what happens if precipitation increases? Well, if the input increases, all of the other systems are going to see a potential increase. More intercepted storage, more infiltration, and with the precipitation increasing, then it might exceed that and cause more surface runoff, more through flow preceding that, and then also groundwater flow as well increasing. So overall, the channel flow might increase too. Next, what happens if evaporation increases? Well, when you think about it, if evaporation increases, one of the big changes is going to be that the water is going to leave the system. So we're going to have more evapotranspiration overall. So that's water leaving the system. And we're going to see maybe less water in stores such as surface store, soil store, and the channel store because it's going through evaporation. Also, potentially less water in the vegetation store as well. What happens if it rained a lot yesterday and it rained again today? So, what we might see is that the soil has gone past its field capacity. It may be oversaturated. The percolation rates might be working at its maximum, but the level of the water in the soil might be too high. Therefore, we might see a reduced infiltration or no infiltration rate at that stage. And in the drainage basin, it would be quicker to lead to surface runoff and an increase in channel storage. So the impact of the vegetation type on this as well. Definitely when we see any area that has a climate that should have a dense forest. If it does have a dense forest, it tends to lead to high interception, high infiltration, high evapotranspiration, and low runoff. This means that the amount of water in the stores are very high. Whereas grasslands, we can see that it's going to stop the rain potentially as well. It has the chance for interception. And infiltration then will be moderate. The reason why dense forest is so high is because there's enough interception to sort of block that water, give some time for the initial infiltration to happen, then the water can come down afterwards and also infiltrate. So it just slows all of these flows down and makes sure that not too much ends up as surface runoff. So with the cropland, then we can see that it's variable because we can see that crops will only actually grow to quite an extent at a certain time of year. All crops are sort of different. So the interception may or may not be there at any one precipitation event. Unlike grassland and forest, while they can change seasonally as well, we can see that the chances of them then infiltrating and interception, or sorry, causing interception and increasing infiltration, there you go, that's why you got to learn your words right, is going to be decreased compared to dense forest and grassland. Where we see areas that have gone through deforestation or just a climate zone where it's quite bare, there'll be very little to no interception, which means there's very little to low infiltration. This is because in a lot of cases, the capacity for the infiltration is so limited by the soil and it could be damaged due to it being bare or going through deforestation stage. This means that the infiltration rates can be very low. Even though this kind of thing can happen in a desert area, we might see low evapotranspiration rates, but most of the water then goes towards the runoff. So we can see that the highest level of runoff is going to be with bare or deforested land, with the lowest in a dense forest. So when we really think about it, when we're thinking about the control of water in a drainage basin, but we're also thinking later down the line when we'll be talking about floods, we're looking at what's going to cause surface runoff. Because surface runoff is going to lead into the river fastest, which means that the river is going to react very quickly to any changes, such as precipitation. In this case, we can see that increasing surface runoff, we could get a steep-sided valley where the water just isn't sitting on top the way it should, so suddenly then it might just flow over the top and less chance of infiltration. Also, in a lot of hill areas, we tend to find that the actual amount of soil capacity is a bit lower. We have impermeable rock, which is obviously going to lead to a rapid surface runoff and less infiltration. Thin soils, as I just mentioned too, is another reason why there would be a limited infiltration capacity, and we would see more surface runoff. Urban areas are often impermeable, which leads to more surface runoff. Saturated soil, antecedent moisture, meaning that there's less capacity for that soil to take in any more water. So during a precipitation event, again, leading to an increase in surface runoff. The high water table has the potential then to reduce the amount of infiltration and percolation. So this causes like a kind of blockage then in the system. So when we see the water table coming up to here, for example, it might also create surface springs. Like here, we would see the water just flowing out off the ground down towards the river. So during that stage, then we have less space for water to infiltrate and percolate. With deforested areas, then, we've already mentioned the impact that this can have and why, and it does have quite a severe impact in both our sections on flooding and drainage basin stores and flows. In this section, then, we're going to talk about a storm hydrograph. We're looking at how the river channel in the drainage basin reacts to a storm or an event where there's precipitation. So first we got to think about river discharge. This is looking at the volume of water passing a particular point. Like let's say that point is right here. So what we're imagining is that we have to find out the area by getting the depth and the width. So we're going to measure down all the depths. We're going to have the width and we're going to get a cross-sectional area, which means we know that there is this area here, right? This area then is the amount of the river where water is passing through, and then we're going to find out how much water is passing through there by getting the velocity. So by doing this, we know how much water is passing this point per second, and so we know the cubic meters per second. So that's actually what we're talking about when we say discharge. In any one river, it's the amount of water passing that point. Now, we put this onto a hydrograph. Now, hydrographs are not always going to come up, but they're a really good way to understand this. But you have to be ready to discuss them too. So there are essays coming up that are just about what influences a hydrograph. So right now we're looking at discharge. There's the cumex per second, and we have time passed since precipitation event. So 12, 24, 38 hours, or 36 hours, and so on. Now we can see that there hasn't been a precipitation event here, so the river just kind of flows in a normal state. It stays fairly level, nothing changes. Now, when we do have a precipitation event, then the drainage basin is going to react. We're going to see that the channel storage is going to increase, which causes the discharge to increase. That's going to reach a height, and then it's going to start to return to normal. We have very particular terms for these. Again, it's more vocabulary, but it helps you just to, write very effectively and concisely, and the examiner will know exactly what you're talking about. So here we see the rising limb as the discharge is increasing. It reaches what we call a peak discharge or peak flow. And then we have the recessional limb going back down to its original base flow. What we're looking at then is also the lag time. How long in hours did it take to react to the precipitation event? So the basin lag time then is going to be the point from peak precipitation to peak discharge. Okay, let's have a look at a couple of examples. But before we do that, let's just see what actually makes up this change. So we imagine what we had before, base flow in the groundwater flow. Through flow is coming through the soil, and the overland flow makes up the largest amount of additional water being measured in the discharge. Now remember, going back to our diagram, that all three of these flow into the river and add to the river discharge. So they've all increased, but note the way they might all actually happen a little bit differently. So some are very slow to react, like groundwater storage, and then the overland flow is much faster to react. So they're the main two that are going to make a big difference here in the change. So let's look at this. A comparable one with impermeable, permeable surfaces. We imagine sort of like a forest or a garden style here where there's going to be expected to be some infiltration. This is permeable. Water is able to permeate through the top, and then impermeable surfaces like the houses on an urban space or the paths or the roads are all built to get water out as fast as possible. So this surface runoff then may flow into the river very quickly, whereas this one in the forest, we go to see that there's a lot of infiltration, percolation, groundwater flow, not so much surface runoff. So the impermeable, we see a rising limb that's very steep. So it's very steep. It rises up to a higher peak discharge than the permeable section. So it's a much higher peak discharge, and we can see that the lag time is very short. The distance between the peak precipitation and the peak discharge is quite short. But then it also reacts in quite a way that it goes down very rapidly too. So by the time an area that has a permeable features, like a forest, is reacting to it, it's already almost back to normal flow here in the impermeable section. So then we see the reaction of the permeable section. It's much slower. The rising limb then is much more gradual. The peak discharge is lower, and the recessional limb then returns to normal much slower as well. So the lag time is much longer in this one because there is all that water going into the different stores and flows. Overall, then, you might have in a hydrograph the precipitation might be there, it might not be there. So don't worry if it's just the lines and you need to think about it from there. Here we can see deforested and forested. It's a similar idea again, that an area that's gone through deforestation will have less of a chance for high infiltration rates, more of a chance of high surface runoff. So we go back to that table where we can look at what increases surface runoff. This causes then a steep rising limb again, big peak discharge, and then a slower lag time. Not so much as the completely impermeable surface, what we looked at before. The forested land, then we see it just reach a more stable point. It stays on a peak discharge for a little bit longer, and then it's slow to return to normal. Its recessional limb there being very gradual as well. So we can imagine that if we were going to use this storm hydrograph to think about the threats of a flood, well, let's say that a river might be at a point where if their discharge is 3 cumex a second that it would flood. We know that one scenario it would flood, right? The deforested area. So we can see that in the hydrographs as we study them. Now, we mentioned again with the surface runoff how steep and gentle gradients can impact the amount of change in the discharge over time. For steep and gentle, we can see that steep ends up with a higher peak discharge and a slightly shorter lag time. So it might still have to travel the same distance, but there's just much more water flowing down. So a greater volume in this case. And we can see then the reaction of the gentle slope just takes a bit longer, but also the peak discharge overall. There's lots of water now in the soil water store, the groundwater store that doesn't make it down into the river in the gentle profile of the valley. Okay, looking at size now, we can think about drainage basins being very different in shape and size all over the world. Earlier on, we had a look at a graphic showing the Amazon drainage basin, and we saw how huge that was compared to neighboring major drainage basins as well. So there's extremes in size. And what we might see is overall the capacity. The larger river might just have a far greater capacity uh, as as would be expected. If they got the same hours of precipitation, we can see that the small drainage basin is more likely to react and reach its peak discharge quicker, even though the bigger drainage basin gets to a similar level almost at a similar time. But this continues because it has a greater volume, a greater number of tributaries. It takes longer for the drainage basin to react because the water has longer to travel. So it must come down then and all join down into the main river, and all the tributaries might join in there. So we can see this related to a much greater peak discharge, but it also has the channels to hold them as well. The shape then is quite important. So here we're just looking at a sort of more circular, rounded one where we have a greater distance for the water to travel. But also, as we just mentioned before, in a lot of situations, this means that there's going to be mega confluences where lots of the water is arriving at one point together, which means it's going to surge together as well and be a bit delayed in terms of its lag time and then lead to a much higher discharge. The elongated basins, then, you might say that they might take time, sure, to come from this area. It's so far away from where we might measure the discharge, where the water's leaving the river and the estuary is. However, we can see that it's more uniformed, right? So water coming from this area will join, then it will join here, then it will join here. So basically, you would see regular intervals of big surges of water going through. So it might look something more uniform where the peak discharge would rise and then it would sort of plateau and or maybe just go up and down for a while and then go back to normal. Whereas on the big one, we'd see a very delayed reaction and then there would be a bigger surge and then it would return to normal. So circular peak, elongated peak, big surge, and then general surge on the rising limb, much higher peak discharge, and the lag time then being spread out over a much greater time. Okay, if we look now at the drainage basin density, the idea of the drainage basin density is the total length of the streams per unit area of the drainage basin. So higher density is like this one. We have loads of tributaries, loads of established rivers on a drainage basin that is the same size, but we can see it doesn't have as many rivers. We're going to see this having a low drainage basin density. And we can see how the reaction in the hydrograph happens, where not too much later in peak discharge, or sorry, in lag time, but our peak discharge is far lower. So this is because the rain can fall anywhere within this drainage basin and it could go through interception, you could go into the soil water, go through flow, groundwater flow, and may take a much longer time to actually reach the river. So therefore, it's not going to have that immediate effect in maybe 72 hours overall. Whereas if it rains in the exact same places in the high drainage density basin, we can see that it has the potential to reach a body water, so surface runoff into a channel storage and be a part of the channel storage much quicker. So going back to that table, the idea of surface runoff then is incredibly important to help explain that, why these things happen, the different elements that can be in the drainage basin, whether it's physical properties or whether it's human enhanced changes that were made. This then has a knock-on effect to the hydrological cycle. When we come back into the flooding section, we are going to talk about this quite a bit. The annual hydrograph then is a different idea. So we're looking over months, not just after one precipitation event. The idea is that we can see seasonal changes, we can understand what to expect, and we can compare it with other river regimes, which is quite important, other drainage basins. And we can also assess then flood risk and drought risk. So take a minute here. We've got discharge in QMAX again, but down at the bottom we have the months. You can see that there's extreme changes in the total discharge in terms of the numbers, but also in the graph itself. Take a minute and try to guess why such a sudden change happens around March and April, and why there's such fluctuations in June, July, and August. So here are a couple of reasons. One, we could see that there could be snow and less glacier melt up in higher mountains. And we could see the sudden addition of months of very little amount reaching the river. So December through to February, this is where everything could be falling as snow as precipitation. And this is why we see the lowest discharge during this period, during that time. So all of the water is actually locked up in snow or ice. And then come the springtime, there's a sudden thaw and a melt, and we see all of that water flooding down from the mountains into the river. So after that, we can see it peaks, dips, and it comes right down then and kind of levels back out again. We can see maybe certain drops in this as well because there's a lot of vegetation growing. There's a lot of water used for irrigation into the farming areas, for example. And then we can see fluctuations until maybe the end of harvest. So this is where we could see precipitation events being quite high in the hotter weathers, if this is the northern hemisphere, and maybe leading to higher precipitation events during these periods too. Yeah, so lots of changes throughout the year. Now it just depends on where you're studying. Of course, this could just be a sort of like a monsoon season where there's a much higher precipitation level for a certain period of time. Now, if we look into the climate zones, then they each have their own characteristics in this case. Equatorial rainforest is going to have a hydrograph that's quite flat and consistent because it rains all year round and the vegetation is there all year round, which means it can control the rates. The only thing that can change that then is any of the permanent changes that humans can make or any environmental damages or hazards. Mediterranean, we see higher hydrographs in the winter and low in the summer. This is because there's a lot of dry seasons in the summer with little precipitation, whereas the winters then can be quite wet and continuous with snow and rain. Alpine mountains, we just kind of looked at one there, sharp peak in late spring, early summer, and snowmelt driven discharge. Monsoon climates is one peak season, and it can be sudden, but it can also be prepared for. There's also a lot of people within that area where we start to see them utilizing that monsoon rain to be able to hold more water during their dry season. Temperate maritime, then we see multiple peaks and troughs because of rainfalls, but also we can see parts of the year where things might be frozen. You'll have a lot of trees that lose their leaves, and we don't have a lot of transpiration then until they grow back again. So different seasons are impacting, like a 4 season climate zone is being impacted by lots of different factors. The annual soil moisture balance. So what we're looking at here is, again, we've got the months of the year at the bottom. And we've got the mean precipitation and the mean evapotranspiration. So it's this combination. And within the soil, then it reacts to this. So we're going to start at the beginning of the year, and it's here in the green, and it says it's a soil moisture recharge. During this period, precipitation is greater than evapotranspiration. There is more rainfall going into the drainage basin system than there is leaving the drainage basin system. So this means that the soil is receiving more water than it is losing. After that stage, we get to the soil moisture surplus. This is when the soil is at its capacity and it's in a state where it has enough water. We see the evapotranspiration rates then increasing as we're coming into spring. And just around that time where we get increased temperatures, we have a surplus of water. In summer like this, we can then anticipate that there's going to be far more growth of plants. So plants are using the temperature change also, and now we see the plants going through more transpiration. So evapotranspiration skyrockets during this period, and this is why in a lot of climates this is the springtime where a lot of crops are grown and a lot of vegetation in the natural environment grows as well. So we see that the soil moisture surplus then is helping and it's going into the utilization period. After this stage, then, a lot has been used up and the amount of evapotranspiration is still quite high. The precipitation reaches an all time low, and now we start to create a soil moisture deficit. So there is sort of like a mass die off then of vegetation and, yeah, a loss of things like leaves for the year. And we see precipitation increasing again. And then the soil that has gone through a couple of months going into a deficit and losing its moisture now goes into a recharge mode from October. And this brings us back to the start where the recharge is ready for next spring. Okay, that's Unit 1, Part 1, the Drainage Basin System. Hi everyone, this is Brian. If you're really enjoying these videos and they're useful, please do like them, leave some positive comments, and make sure you subscribe. By doing that, I can keep making these videos and helping more and more students. Thanks very much. This is part 2 of Unit 1. It's looking at river channel processes and landforms. Throughout this, our learning objectives is to help to explain the process of erosion, transportation, deposition, and other processes. We're going to describe and explain the formation of major fluvial landforms from upper to lower course, and we're going to assess how river characteristics change downstream and influence the landform developments. So let's start off by going into just general characteristics of the river. So we can define and look at a river here, and we can think about describing its width, depth, banks, and beds. So these are the width here is going to be quite narrow. The depth is very shallow. We can see the rocks here. The banks are very, very high and steep here and also here. And we can see that the river bed is how we would describe very rough. So it's made up of lots of different large and small pieces of sediment. So you can see the water has to flow over quite a lot of uneven surfaces. Now, if we move downstream, we're going to start to see a change here. So now we can see the width of the river is much, much wider here. The depth, well, we can't see the bottom anymore, and we can assume that it's much deeper with such large boats in it. The banks are going to be a little bit smaller than we saw before and more even and flatter. And the riverbed, even though we can't see it, is indeed a lot more smooth and is made up of more finer sediment. So that changes as we go from the start of the river by the source in the upper course all the way down the river to the lower course. And we can see like the little cross profile sketched out here. The discharge in the river then is very different. The discharge increases drastically as we go down the river channel. So the upper course then is defined as where we start the river. Usually we see many tributaries coming in through the upper course, and this is where a river really begins. So while you might think about a waterfall as having a huge volume of water, it's nowhere near the same amount as it will be down the other side of the river. So it's quite a turbulent area as we can see the water moving around all the different rocks and stones and even down waterfalls. So high amounts of turbulence here in the upper course, narrow, shallow streams and rivers. And we're right up here at the beginning of the watershed where we have our water source. Now, if we go down further, we can kind of see areas like here, for instance, might be an upper course. There might be a river running down here, but once it reaches a much flatter land and multiple tributaries and streams run into that, it becomes wider and we can see it becomes deeper in places. In some places, it's still quite shallow. In some places, it's now much, much deeper. So the river is noticeably wider, but the landscape around it is much flatter. So again, upper course down into the middle course. Now the middle course continues and the landscape usually gets a bit flatter and the river again can get much wider. So we can see huge estuaries here at the end of the lower course, huge areas of flat land then with very small river banks and very flat organized riverbeds. Now, getting the cross profiles then of each one is just something to get used to. So we imagine if we came here and we measured across how the depths would change and how that would look if we measured it properly. So cross profiles change as we go. As we mentioned in the upper course, we're going to see steep valley sides, V-shaped, more narrow valleys, and shallow channels as well. Middle course then is still steeper than the lower. It's going to be flatter than the upper, and it's going to be much wider. So we see that change, and then finally very flat land with big wide channels at the end in the lower course as it's flowing out into the sea. Okay, so we can have a look here. For example, again, we have maybe upper course here. We might call this the middle course as the tributaries come in, and the lower course down here where we'll have the full volume of the river. The Bradshaw model then is not just a model to talk about rivers, it's also something you can use in your essays as a part of the theory. So you reference the Bradshaw model in your essays. That's part of what we teach in the examination skills section as well. So go check that out if you're interested, or the exam prep program. So we have upstream or the upper course, we have downstream, the lower course. So the river is moving in that direction. So a few things we expect to see. The discharge is going to increase. The occupied channel width is going to increase. The channel depth is going to increase. The average velocity is going to increase, and the load quantity, meaning the amount of sediment that it carries in total. So as we're going down to the lower course, then we also see load particle size decreasing. So the sediment up here can be very large, but very few. And then later, the sediment size is going to be very small, but we're going to see lots of it. The channel bed roughness will decrease. So just like I was showing you there on the river bed where we had lots of angular rocks that the water had to move over, we're going to get this in the riverbed roughness. So as we go down, the bottom of the riverbed then will be much more smoother and have less turbulence compared to the upper course then, which might have lots of jagged rocks and be hard for the water to pass through. The slope angle then, or the gradient of the river, is going to decrease. So we saw things like waterfalls in the beginning to show an extreme example, all the way down to very flat and easily flowing rivers in the lower course. So the Bradshaw model is something you can reference and then discuss any of these things according to the Bradshaw model. All right, let's get into our processes. So we've got hydraulic action. This is the idea that it's the force of the water itself hitting the river bed, the river banks. It's causing then the changing of the river and breaking off parts of the river banks or beds. Now, it also goes through a point where you have the pressurization of air in it as well, and this leads to cavitation. So there's going to be forces and causing joints and cracks to open up, and it eventually then will wash away part of the riverbeds or banks. Abrasion then, or corrasion, as you might see it in some places, is when the river has enough velocity to pick up a piece of sediment, and then the rolling of the pebbles or the stones ends up causing an abrasive motion. So we start seeing things like bedrock sculpting, where it can create hollows in the ground and begin to erode it out. We can also see in more angular examples here how it can make it much, much smoother. So abrasion then has the ability to erode away the river bed and the river banks, just depending on which way the current is going. The idea then of attrition is that sediment size, like we looked at, and according to the Bradshaw model, we would say that the particle size is decreasing as it goes downstream. So as part of that, we expect attrition to happen. This is where the rocks start off much larger and more angular, and they start to break off each other as the river moves them. And this eventually puts them into smaller, rounder pebbles and then breaks it down into even finer sediment, into sand and silt. So if you're ever, like we're on a riverside and you've picked up a very flat, rounded rock and you've been able to skim it off the top of the water, that's usually because it's gone through the process of attrition. So attrition is really important then to get sediment from the upper course down into the lower course where it can be deposited and can also create new land. So we've got abrasion, hydraulic action, cavitation, solution, and we mentioned attrition. that's not there. But solution then, corrosion, this is chemical erosion. So dissolving minerals inside the river beds and banks, like we talked about before. Limestone, for example, and chalk are more vulnerable to this. So things can dissolve, like if you have an energy tablet or a vitamin C tablet or something you can drop in water and dissolve, taking a solid into a liquid. So that's what's happening here as well. Okay, when we think about transportation, then there's different ways. We'll start off where we left off, is just the idea that minerals can be dissolved and then they can be carried away. So if they've gone through the process of solution and erosion, it's also called solution when they transport those minerals down the river. If the sediment is very large, it's going to roll along the bottom because it's too large for the river to pick up. This is known as traction, a rolling or sliding motion with pebbles or boulders. The saltation then can happen if the sediment can be picked up. It then takes less velocity to be able to just carry it as it bounces and continues on with some momentum. And then finally, suspension then is going to be the finer minerals, the silt, the clays that are being suspended in the river as they're being carried out. This is often why we would see that rivers that are reaching the end of their drainage basin and we see them going to the estuary, they often look very murky or very dirty, and that's often because they have a lot of sediment in suspension. They also might have a lot of pollution by then. Okay, so we got the different types of transportation. Again, going back to your vocabulary sheet, you should be able to look up the specific 3-mark vocabulary responses for each of them and learn those and make sure you're ready to use them. Deposition then occurs when velocity and energy decrease. Okay, so the river is decreasing. Let's say on this side of the river over here, if you studied IGCSE, you know we're looking at a meander, and there's different velocities. So on this side of the bend, there's less. So there's a more shallow part of the river. This river is widening out. So not all the energy can maintain the same amount of power. So most of the velocities over this side, and here we get less of a lower velocity. So we see then friction, and with friction, we then see a reduction of velocity again, and this may cause sediment to build up, as we can see here. So that's often one of the main reasons. And then from there, sedimentation can mean that a lot of these small bits of sediment that all join up together over time can be compressed and they can join together then and form very hard layers of more permanent land. Patterns of flow. This is a bit of a tricky one to visualize, but we've got different flows within the river. Now, laminar flow is the idea that there's no mixing, that it's a smooth action. Usually, you're not going to get this in normal rivers. So, in an actual confined environment, in a scientific experiment, we can create a flow where the river should be the same at every level as it's flowing. There shouldn't be any interruption from the top, from the sides. There's minimal friction. This is quite hard because water always has some sort of friction, like on the edges here of this glass container, it may undergo quite a lot of friction. So low energy environments usually can lead to more laminar flows in places. But completely laminar flow, then not really in the natural environment. Then we can think about turbulent flow. So turbulent flow then is happening where we can see vertical or horizontal eddies. So these are currents that are moving down or they're moving side to side on the river. So these create then a lot of hydraulic action potentially. They can cause sediment like here to get picked up and lead to a lot of abrasion as well, and can increase the erosion in these regions. So we often see this in more shallow waters then where we have a high bed roughness causing those changes of the river and causing the eddies to swirl around there and create turbulent flow. Helicoidal flow then is one that we'll talk about again at great and attach it to meanders. When we're looking at this, the water is typically moving in a spiraling motion, as we can see here. So usually it typically happens when we have bends in the rivers or meanders, and what we find is then we see it's a cross current. There's one main current called the thalweg, which we'll go into when we're talking about meanders. And what this does is it starts to transport sediment from one side of the river to the other. As it's swirling around it, it's able to have more velocity to send sediment over to the other side. So it has a role to play in very specific parts of the formation of the features. All right. So our upper course, middle course, lower course. We already talked about some of the key characteristics. So we're beginning with steep valley sides. They're going to be narrow and shallow, and we're going to see lots of turbulence. Often this leads then this turbulent flow to strong eddy currents, and we see vertical erosion. So vertical erosion means that the landscape will begin to decrease. So if you imagine a long time ago, the river was here and it was just a little river there. So narrow channels, high bed roughness, lots of sediment. So we see vertical eddies on the riverbed, and this causes vertical erosion. And over time, then the sides of the valley will have reacted by becoming weaker without the structure and would have caused a bit of a landslide in there. So this means that the new shape of the river would have been something like this, and it just continued and continued. So usually in the upper course, one of the features we can see is a V-shaped valley. So we can see it's quite common all over the world in the upper course in the mountains. Now to show you the extent to which this happens, this isn't one of the official necessary features, but we can see here with potholes, which is a really good way to remember abrasion. So cylindrical hollows usually found in the upper course, close to areas where waterfalls form. So we have irregularity, obstruction, we have a high amount of turbulence because we have such high bed roughness. The occupied channel width, then all of this combined creates then eddies. So this one here is creating a vertical eddy which is going down and is causing maybe hydraulic action over this barrier, and this is causing vertical erosion in the area. So the vertical erosion opens up a hollow, and the velocity in the river is enough to carry sediment into the hollow, and this creates then a swirling motion. That swirling motion then causes the pebbles or the sediment to spin around, and this increases the rate of vertical erosion, and this is known as abrasion. So abrasion occurs to open up these potholes even further, and then it continues to move down vertically over time. So through the formation of potholes, we can see how turbulent flow, vertical eddies, and abrasion can be used to explain the formation of this natural geological feature. Next, waterfalls. And I'm just starting this with a description because in the past they have asked questions to describe and explain something. So after you've explained this perfectly and you've written out your definitions and you've followed all the short questions that comes with this course on the Geography Academy, you may find yourself really capable of explaining how a waterfall is formed. But you might be at a loss because you might not have practiced how to describe one. So a waterfall happens along the course of a river stream. It falls vertical or at a steep angle towards a lower level into a plunge pool. It's often found in the upper course. Now, that's not rocket science of a description. Most students who have never studied geography can make that description, but you'd be surprised at how many people it catches out. Now, we're going to see very similar characteristics actually with our waterfalls today because we're only talking about really one type of way that they're formed. And in this, we see that there's an overlying bigger slab of rock. Underneath, there's a bit of a hollow, and it might be cut out a little bit, and we may see the remains of some fallen rock beneath it, and then we'll see an area that has deeper water here. So again, let's have a look at this different place altogether. We've got one level of rock here that the water is falling from. Then we see there's a gap or a hollow underneath, and then it curls back around, and we can see darker pools of water underneath it. And we can also see some bigger rocks nearby that might be indicating previous changes in the landscape. Now we're going to go on to another one. Now this is a completely different one, and what we can see again is, yes, it's falling from one place to another as we expect. And there's a bit of a hollow in the back here, but we can imagine that the river here gets much, much deeper, and then it appears to get brighter because it's more shallow. So it gives us that kind of a shape, and that's what we're roughly going to be using in our diagrams. We can also see the change in the scale because here are some people standing so close to it. You can judge the absolute scale of this. So whether it's a very small waterfall or a very large one, they can follow the same formats. Also note how we're in the upper course and we expect to see the idea of vertical erosion. So here's a good example here where we can see that the shape that the waterfall is coming from is very much like one we would expect in the upper course. Also have a look around for other factors. Around this stage here, the rocks look all quite similar, but they might be different, and we can see evidence that there's maybe a switch in geology at certain sections of these gorges. Okay, this is probably a good time to bring in the idea of hard and soft rock. So hard rock is more resistant to erosion. Soft rocks are usually less resistant to erosion. We talked about this in the previous section, where we can have igneous, sedimentary, or metamorphic rock. So the more we drift towards the sedimentary rock, the more we drift towards more of a softer rock. So we can see it here like a sandstone, something you can break apart with your own bare hands, and you can break it into smaller and smaller pieces. Just like it was formed by smaller pieces coming together, it can also be broken up like that. And this often leads then to an increase in the rates of erosion. Then if we have a look at the more hard rock, we could look at, say, something like a granite, an igneous rock. And as we talked about before, the formation of this is so tightly packed that things like hydraulic action, cavitation is just not going to happen as much here. And the changes to this rock is going to be much slower. So in the initial formation, the idea is that we have a cap rock or a hard rock that is more resistant on the top and a weak underlying softer rock. It may start at some stage some vertical erosion due to turbulence, vertical eddies, things we talked about before, and this is going to cause then a change in the landscape. So we've got these two rocks, and now the erosion is going to be increased in the softer rock. In stage two now, we can see that the waterfall has sort of been formed. What's happened now is the hollow's being created because the erosion rates of the soft rock is much, much faster, which leaves an overhanging surface here. Now, as the water is able to fall down more directly, this is going to create lots of hydraulic action, and the swirling and the broken down pieces of sediment will eventually cause abrasion. So these two are going to make a much deeper plunge pool, that area with greater depth that we looked at in the picture. So this is the soft rock being eroded, and now there's a concentration in one area that will erode faster than the areas around it, creating a deeper part of the river. So this undercuts it and leaves a layer of hard rock suspended above it. Over time, of course, that can collapse down and the waterfall can retreat back. So the harder rock now collapses and it's added into our area at the bottom. It can be broken down eventually with attrition. But as we also saw in the pictures, there's often evidence of different types of rock and different sizes around the waterfall. So this can go in, and through attrition, it could be broken down eventually and add to the abrasion, but it collapses and it retreats. Now, if this happens over time, if it continues to retreat upstream, what happens is it continues back and it leaves these gorges behind, which are the very long walls here, narrow columns, and you can see there it can go right back and follow a course. So steep-sided gorges, and we can see that it's still made up of the same geology all the way along, so it's quite universal. And yeah, we tend to find that it's just that retreat back up the gorge there, creating a narrow valley. So this would be the view, perhaps, if we were looking from up here or up here, and we're looking down at a gorge and we're seeing all the steep sides of the valley now. So this is where the waterfall could have been before, and it's retreating all the way back up and leaving this steep valley behind it. And even still, we can see some smaller waterfalls and little weirs which are able to erode away still vertically, which might open up a much bigger gap in the future. For now, though, they're not quite as significant as the other ones that we looked at. Again, here we've got the steep gorge valleys, and we've got the waterfall then at the end, and we can see it coming down. This one isn't actually undercut at this stage, so it's quite interesting to see it at this position. Eventually, that'll become a bit more undercut and will open up a bit of a hollow here. But still, we would expect that the water is deepest at the base. We go back to our original picture and now we can see everything we saw before. There is potentially a cap rock above it because we can see there's some difference there, although the rock here and there look quite similar. So it might not be the exact case as we talked about before, but as I mentioned before, there's different lines of geology there. So there could be something like that happening here too. This is going to be undercut. It's going to be deeper, get up and be a bit more shallow. We can also see where probably the previous waterfall positions were as well. Most likely, if we continue on our way through this gorge, we'd also find more waterfalls. An example of this is High Force in the UK, where it has the Weinstill dolerite cap rock and it has a less resistant carnivorous limestone underneath. Again, we've mentioned this rock now several times as a sedimentary rock that is quite permeable and porous. So this one here, 22 meters in height, which is very large, and the gorge is half a kilometer long. So you can walk along these steep gorge walls for half a kilometer before getting to the waterfall itself. Much more deeper, turbulent, and more hydraulic action there at the base. So, what do you have to do with all this information? Well, obviously, there's the short questions that you can answer on the Geography Academy, and that's good. You can also look over all the vocabulary, just double check you're good with all the processes, everything that's been mentioned to this point. If you find there's a couple of difficult ones, follow some of the guidelines I've told you about making your own vocabulary flashcards as well. Have a look at the revision notes that I've posted too and just double check them and see if it makes things easier for you. Then the final step is to explain it all in your own words perfectly. Go get some great diagrams or create your own. And by creating something, then you're making a more lasting, powerful memory. And it also shows you the extent to your knowledge on the subject. So for each of these major features that are on the syllabus, I would expect all of my students to have written them out perfectly and be able to revise it in a matter of seconds. Okay, those are our features in the upper course. We're moving on to the lower course now. In this image, we can start to see a change. We see all these lines of snow moving down, which are indicating to us upper course sections. These are all tributaries feeding into a middle course section. And we can see the middle course section is a little bit flatter where snow has accumulated, but it's still also meandering side to side a little bit. So characteristics are beginning to change. Part of those characteristics then is the discharge increasing, the angle and the gradient of the slope is decreasing too. So in that sense, we would expect then that it's not going to be as turbulent in this situation, and we're not going to see as much vertical erosion as we did in the upper course. Okay, the first feature to mention here are the Meanders and Oxbow lakes. So anyone that studied geography before would have been familiar with this to an extent. So we're just extending that explanation and making sure it's right. What we can see is meanders are basically bends in the river. Oxbow lakes then are when part of those bends gets cut off from the river as the river forms a new channel. So for example, the river might want to cut through here eventually. So that would make this the new channel and this the old channel. So the old channel turns into an oxbow lake. Very common in all rivers around the world. So we can see here on a much more wider angle from a satellite perspective, and we can see enormous meanders that are running through here. Lots of green areas around it, supporting lots of agriculture either side of it here. And we can see the way it bends and changes, and we can see islands in the middle. I don't know if we look closely, if we can see any oxbow lakes here. They could have been dried up a long time ago, so hard to note here. Here we can also see it, and we also get a chance to look at a different version of the middle course, you know. We've got upper course coming down as far as here, and then we are a much different gradient once we enter into this section here. So this different gradient then on this section here is part of the middle course, and we can see now winding meanders. Actually, plural meanders in this area here, just separating and coming back together. We'll talk about that as well as another feature too. So this is a really good example of the upper course feeding into the middle course. Here we can see a much bigger meander, and the thing to note about meanders is they can actually appear in the lower course. They do appear in the lower course. So from the middle course onwards, we generally talk about them as a middle course feature, but they still happen here. Here we can see a huge area where we go for that cross profile again. It comes a bit deeper, comes up here. So it's a similar idea, it's just much larger. Now, the meanders then have a couple of interesting characteristics. So if we look at the wavelength, the belt width, which is between here and here, and then we look at the riffle spacing. So the riffle is the little sections in between the meanders, right? So just around here. And we look at the wavelength. We can see that the wavelength is usually about 6 to 10 times the channel width. The belt width always falls between 14 and 20, and the riffle spacing about 5 to 7 times the channel width, which is quite interesting. So if we increase the channel width, all of these things need to increase, which means that the meanders then become much, much larger, and this will change their sinuosity, the way that they bend. So it's quite cool that we can pretty much mathematically guess then if we increase channel width, what the reaction would be at this point. So let's begin. How does a meander start? It's a hard thing because, well, rivers are in operation and they've started bending a long time ago, but we imagine a perfectly laminar river, right? Now, if anything was to change, like there was a moment of greater erosion of one side, part of the river bank collapses in, and suddenly the river is pushed off course into another direction. Well, it starts off this chain reaction, and usually it's just bed roughness, riffles, pools, so shallow and deep areas, which start to cause this sort of variation in flow and increases turbulence and the velocity on one point. Now, the riffle and pool sequence, we're looking at a variation in velocity and bed roughness. So in one area then we have got an area that's shallow, which is the riffles, and we're looking at that, and lots of coarser material is deposited there, and we see the flow of the river then being spaced out in this case. So usually sediment is carried into it and then deposited, and then we see it is going to be a little bit faster here and a little bit more turbulent. Then it's going to enter into the pool, and when it does so, it may often end up going in one direction and causing it to join and be less distributed. So we can see here then a concentration of erosion and the deepest part here with the pool. So the riffle and pool sequence can start like this, and what ends up happening then is we can see it here. Riffle pool sequence, the pools start to become on what becomes the outside of the bend, and we see more erosion and greater velocity. And when that happens, then the erosion is going to be focused on there, and then it goes to this side here onto the banks, through the riffle section then, and then to the next outer bank. So the riffle and pool sequence in that sense then can be created and can be developed into a meander or a bend in the river. So the line that we talked about there is known as the thalweg. Now we mentioned this earlier and I said I'd explain it. So the concept now is that there's a line of greatest velocity. So if you were to stand in the river on the outside bends here, you would experience the highest amount of energy, the greatest depth, and the greatest amount of erosion. So a higher velocity can lead to an increase in hydraulic action, an increase in abrasion. But unlike what we experienced in the waterfall section, what we expect is that this is going to cause lateral erosion, meaning that it will continue to erode the river banks, and not the river bed as much, and it will cause it to spread out. So that's what's happening on the outside bend. There is a greater amount of erosion. It's a lateral erosion, and it's causing then those banks to retreat back. So similar on the edge, if we were to look at the side profile, we would see that the outside bank is over here. And what would be happening then is there would be a much deeper, faster river velocity coming into that corner and causing it to be undercut through hydraulic action and abrasion. And eventually this creates then the collapse and the retreat of what we call the river cliff on the outside bend. Okay, we're going to talk a bit about deposition. Now, we didn't talk about this during the processes stage, So Hjulström's curve is just sort of like the Bradshaw model, something we can bring in just to help us explain something. So here we have to imagine that your sediment size is, let's say, 10 millimeters. The velocity is up here again, and we would say that for something of 10 millimeters, in order for it to be lifted, we need the velocity to be up here, which is above 100 cumex, right? So that's how much it's going to take to just lift it off the riverbed. So there's the riverbed. Now the sediment has gone from sitting on the bottom to getting picked up. That's where we are now at A. So what happens is the velocity then decreases for whatever reason. Maybe the river just widens out very suddenly, and the velocity decreases. So it decreases to about here, and we can see that it's still in the transportation range. So that means it's still being carried, even though the velocity is decreased. It's only when it gets to the depositional line or the deposition line here that it will go back down onto the riverbed again and will settle into it there. So that's the deposition. But now that it's on the riverbed, if it needs to be lifted again, it has to go back up to the point of erosional velocity. So how do we use this? Well, when we're talking about deposition, we can say that the river has fallen below the depositional velocity, and we can refer to Hjulström's curve. We can talk about it with transportation, the idea that transportation can happen even when the piece of sediment has fallen under the erosional velocity. And what you'll note is this changes for sediment size. So sediment size and velocity then are directly correlating into what we would experience: erosion, transportation, or deposition. In stage 3 then, we're talking about deposition. So we've got the velocity, the energy to transport all the sediment load is changed. We're talking about the outside bend here. So we're looking at a little cross section like this. We have X here, we have Y here, and we've just put in a little transect here. So here we've got again, the thalweg is coming in here, lots of erosion, but also remember, we mentioned this idea of helical flow or helicoidal flow, and this will help to transfer more sediment up into the inner side of the bend. There's less velocity, because the thalweg is over here. There's also more friction with the riverbed, and this creates then a perfect chance for more deposition to happen because of the reduction of the velocity. So what tends to happen then is the largest sediment is dropped first, smallest later, and creates then this point bar that gradually decreases. Now what's going to happen when this actually erodes back? Because we expect the outside bend to continue eroding. So if this is the new position of the outside bend, what we would expect is that the river would become too wide, it would lose some of its energy, and it would start depositing sediment even faster, until suddenly you have the same shape of the river, the same width of the river. So because of that, as rivers migrate outwards of the outer bend, the inner bend can also grow at the same rate, and the actual width of the river might stay the same. So this is constantly at work. Eventually, though, what might happen is that the outer bends erode, they get too close to each other, and then we might find a new line of greatest velocity passes through this area. So for a while, it's not uncommon for a river and a meander to have two areas to go and two directions to go. This is one that's just being cut off now, so we see there's very, very, very little flow coming out of this side of the meander. There's still a little bit of flow that's coming inside here, but this is getting broken off. And as we reduce this and reduce this, it'll eventually close off. Sediment will deposit, and then we'll see vegetation growing over it. So that is about to become an oxbow lake. So it gets cut off. Things are becoming more narrow between the two, and eventually deposition occurs, and we'll close it off because it's the point of lowest velocity. Now, that's a general meander we're talking about. We can look at incised meanders, so existing meanders with vertical erosion as well. Or we can see the landscapes rising up as the river is eroding vertically. So both happening at the same time. So that can continue to happen. And in a case like this, what we might find is there's a lot less lateral erosion and more vertical erosion. In other places, we can still see lateral erosion happening as well and breaking through even big areas like this to connect up the river to an easier flow. The next feature here is a braided channel. So by definition, then a braided channel is when we see a channel split into three or more. So we can see here, for example, it's divided into multiple sections all the way across there. So it's multiple channels along one place. This is still happening on the middle course. We can see the upper course ending here and coming down this way. And we can see some of the sediment that's being brought down by the rivers at different times of the year. It's down the slopes here and different processes. So this is a bit different to our meandering channel. And the reason for it is the surrounding circumstances. So if we imagine that these large mountain ranges suddenly go down into a flat plain here, and during the winter, we will see this whole area then is going to be holding a lot of snow all the way along here. So it holds up all that precipitation, locks it up in the mountains for many years, or many months, I should say, and then it melts. When it melts, then huge amounts of the mountain is taken off by all that erosion that we talked about before. There's a large amount then and a large volume of water that passes through. So this means that these very large tributaries that are all down here, they're able to bring large amounts of sediment and quite large size sediment as well. So it goes through that melting season, increases velocity, and then comes down and deposits them all along the base here. So it's a little bit unique in that sense, more unique compared to the meanders, because we're going to see that they have a much more higher sediment load and a huge seasonal variability. So here again, we kind of see it, and we can see similar characteristics because even here we see it goes into a single stream meander, whereas here it breaks into then multiple channels. And we can see all these channels are then divided by little islands here. Again, this is a similar circumstances in a different part of the world. So we have Alaska up in the last one. This one is Patagonia. But the same idea, just different seasonal change. Huge amounts of snowfall into this area. It stays. It also fills up a lot of the basin here as well. And then it'll all melt. And when it does, it increases discharge, which allows it to then bring a lot of sediment down. So while it's going through this braided channels, you have then your high season and your low season. So we can see here as well that some of these islands then become more permanent. They get vegetation on them, and then they are able to maybe resist some of the erosion a little bit more and become more long-term here. So that's the concept. The idea then is that we have seasonal discharge increase. So it might reach a point here, as we can see with the dotted line, and that during that period it might all appear as if it's one large river. During that time, some of the more permanent islands then that have vegetation on it are going to maybe be a little higher off the ground and maybe a bit more resistant to the erosion. And during this time, it's also going to erode away other parts of the islands, like the backs of the islands will change. So when it does go down, after that large discharge increase, when it does reduce back down, what will happen is the carrying capacity then of the water is going to be reduced. It's going to fall under the depositional line of velocity of holding this large sediment. So all the sediment then is deposited. And when it's deposited, it might create new islands and different patterns than what we saw the season before. So this means a lot of these islands are temporary and they can be eroded and changed as the seasonal change occurs. So that's the general idea of the braided channels. Now we mentioned snow being a factor if it's up high and suddenly there's a seasonal melt, but also we can think about monsoons. In some areas of the world, both actually come at the same time. So we can see there then these big changes in the rivers during this period, and this leads to large braided channels. So just to be clear on a couple of different pieces of vocabulary here, the sediment bar then temporary, usually absent, but you'll see it maybe inside an active channel. So this is made up of gravel, cobbles in the river, and is made through deposition. We have the mid-channel bar, so we see this forming and splitting the flow. So they're usually temporary. They could change or they could build up then eventually. And once it builds up and establishes more vegetation on it, we get the river island, which is here. So that can also come as an eyot maybe in some countries and some regions around the world. So that's vegetated and then a little bit more permanent. So braided channels then, if we're looking through here, we're learning how to write about geography, physical geography. So far in the waterfall and the meander that we've looked at, we've tried to do things step by step. And that's the best advice I can give at this stage for when you're just learning. Okay, you don't need to put this into essays just yet. So what you have to learn to do is make sure that you can go through it step by step and introduce ideas then into it. As you go, each step you should be thinking that you're introducing something more and that you're progressing the explanation. So let's go through this one together here. So braided channels form where they receive large supply of coarse sediment or their bed load. They cannot be transported continuously. This is common in glacial rivers, such as Waimakari River in New Zealand, where frost shattering produces abundant sediment. Frost shattering, also another term for freeze-thaw weathering. So that is kind of putting you in the situation where you understand that it's going to be in that kind of a environment where large amounts of sediment can come down from the alpine environment there. Okay, typically found glacier mountains and semi-arid regions where there's discharge fluctuates greatly due to snowmelt, seasonal rainfall, or storms. So if we think about a semi-arid environment that doesn't usually have precipitation, earlier on in the previous section, we were looking at this idea that there would be a lot more surface runoff at that period. So suddenly you're able to carry a lot of sediment because of huge amounts of discharge increase very suddenly through storms in semi-arid areas. Now, again, we're coming into more examples of ones that actually go through that quite a bit. During the periods of high discharge, turbulent flow dominates. Increased velocity, competence, and capacity allows the river to transport large quantities of coarse material downstream. So really focusing on keywords there. High discharge, turbulent, velocity, competence, capacity. So this is really good, concise writing here. When the discharge falls, the river loses both competence, the largest particle size it can transport, and capacity, the total amount it can carry. According to Hjulström's curve, that's how you bring your theory in, larger particles require much higher velocity to remain in transport, so they are deposited first. So that's a good way there to sort of get Hjulström's curve in there and help with your explanation by bringing some theory into it. Now we have the braided channel continue. The mid-channel sediment bars within the channel is created through deposition. These bars are initially unstable and continuously modified by erosion and further deposition. Now they obstruct the flow, forcing the river to split into several smaller channels around these bars, and the flow alternates between turbulent flow, which erodes sediment, and areas of lower velocity where deposition occurs. The river continuously switches between erosion, transportation, and deposition, causing sediment bars to migrate, disappear, or reform elsewhere. This means the channels repeatedly divide, rejoin, and change position after successive floods. So we can see here every sentence is adding something a little bit different, and you can do it just as quick bullet points when you're explaining it there. The result is a wide, shallow network of interconnected channels separated by unstable sediment bars. Some bars may eventually become stabilized by vegetation and develop into river islands, although most remain temporary because of frequent high flows continue to reshape the channel. Now, that is the braided channel formation. Make sure when you're going through these as well, as I advise in the worksheet, is to write out each one fully with the explanation, get your own diagrams or make your own diagrams and get real life examples as well. It's a really good idea to get local examples. I always encourage students to do that. Meanders, every person will be able to find one of those in their country. However, braided channels might be a bit more selective just depending on your climate. As you said, it's kind of very particular circumstances. So what you're often asked about is what is the difference between meanders and braided channels? This is a common question that can come up, including like an essay title. So we just have a look at some of the quick differences. Meanders, more suspended load, just more bed load overall, so all the sediment can be a lot coarser, finer sediment with meanders. Lower discharge variability, meaning it stays the same all year round or more similar. It can spike or drop, but it's not such a big variability as the braided channels. Steeper slopes and less stable, as we can see, because these islands can change, so they're not that stable, and we know that they have steeper slopes, mountainous areas around it. On the other side, meanders have gentler slopes and they're more stable. So the changes that happen with meanders are over a longer period. So just like the meanders, we kind of learned about them as a middle course section. But the reality is you can find them in the lower course too. So in places like Greenland and Iceland, where we have quite a lot of meltwater coming down from the ice sheets and glaciers, we tend to find then a lot of braided channels are able to reach all the way out to the coast, which is the lower course. So that can happen there too at some stages. Okay, moving on to the lower course, then we have flat sides. We're going to expect floodplains. It's the widest and has the highest discharge. So at this point, as we said, we do have meanders. We also see more common is the floodplain. So here we go. A floodplain, a broad, relatively flat floor beside a river that is practically inundated when discharge exceeds carrying capacity. Exceeds carrying capacity, or the channel capacity, I should say, is when the water is going to be able to spill over the river banks and into the sides. So let's have a look. Floodplains then, because they flood regularly, we can see here expanding outwards, they often bring the sediment over the top of the river banks as well. So when it deposits it, it's going to deposit it in an area that's close to the river, and it starts to formulate then certain characteristics. So we'll look at these ones, the floodplains, bluffs, and levees. So levees just being like a higher raised wall like we see here. These are artificial levees, but still the same concept. All right, so a levee then is built up on the river banks over time. What we're going to see then is that the river will flood and it often deposits the largest sediment first. So we think about Hjulström's curve. The second the river is able to exceed its bankful discharge, the second that's able to happen, that's the point in which the river starts to lose energy straight away. So it has maximum energy when it's just about to break its banks, and then once it goes over the side, it loses energy straight away. Larger sediment deposited first, then the next size sediment, then the next size, and the next size. And once it gets down into the flatter area, then it's usually silt or finer sediment. So this builds up a sort of shape, what we would think about with the levee, kind of high, much higher towards the river bed and or the river bank, and then it flattens out as it goes and moves away from the area. Now, the one thing to note about this image is if we imagine this, if we're going to go back in a geological timeline, which often we have to do with these features, we can imagine here how this is the original valley. So over time, this valley has actually increased in its height. So when you think about it, like with archaeologists, they have to dig into the ground to find the remains of maybe old villages or settlements. And that's because over the years, often many settlements were beside floodplains and flat land close to a water source, and lots of sediment will have been deposited over it. And over time, that starts to compress. So it turns into more compact rock over time, even sedimentary rock over time. So this land is building up. So each time it floods, then it's adding an extra layer to that, and that just continues over time. So because of that, the natural barriers here are then filled in, and suddenly we can see this kind of steep wall on either side that's left behind, sticking out, remnants of like the old slope that would have been underground. So this is the river bluff. Now we talked about meanders migrating. So if this one was to migrate out this way, it would generally get to the river bluff, and then this would kind of stop it from migrating any further this way, and may actually encourage it to migrate back the other way. So then inside the floodplains, the meanders can actually migrate from side to side. The river bluffs provide the edge of the floodplain, and then the floodplain itself is built up over time through deposition when the water is overflowing into the area there. So that's the general concept. Simple diagrams like this are helpful just to really emphasize the size of the sediment and even just exaggerate that sort of a shape of the levee itself. Okay, and then simplified ones like this also help, just showing the buildup over time. And also what we note here about the floodplain is the floodplain is very flat. So even though the original valley may have been not so flat and not so straight, over time all the deposition actually just covers up all those little hills and makes it much, much more flat over time. Okay, so let's have a look through again and just see the way we can write about this as we're just explaining it. It's not quite essay standard, but it's just good explanation. So meanders will migrate laterally due to erosion, hydraulic action, and abrasion on the outer bend, and deposition on the inner bend. So we know that already from our last section. During periods of bankful discharge or flooding, the river overtops its banks. As floodwater spreads out, velocity rapidly decreases, as per the Hjulström curve, again mentioning the theory, causing deposition of fine sediment or fine alluvium, clay, and silt. Repeated overbank flow deposits layer of sediment, creating a broad, gentle sloping alluvial plain. The floodplain becomes wider and thicker over time as the river continues to rework the valley floor. Over time, the widening floodplain contrasts with the remaining steep valley walls, forming bluffs. These often coincide with resistant rock outcrops or form where there's vertical erosion has slowed and lateral erosion dominates. Bluffs may contain river terraces, remnants of previous floodplain levels, indicating past river downcutting due to base level changes or climatic shifts. The levees then coming in here, when we have the river floods, energy drops suddenly in the channel edges, so heavier, coarser sediment like gravel and sand are deposited first, close to the banks. Finer sediments like clay and silt, which require a lower critical settling velocity from the Hjulström's curve, are carried further and deposited more distally on the floodplain. Over time, successive floods events cause coarse materials to accumulate near the banks, creating raised features. These levees can grow higher than the floodplain, temporarily confining the river and even causing raised channel profiles, as conditions known as suspended river. If breached, especially during extreme discharge, these levees can lead to catastrophic flooding. A little bit extra there at the end, putting it with some diagrams. The only thing that could be missing from this is also a good habit to get into as well, is just to actually introduce where you're going to find them. So floodplains and bluffs are usually found along the lower course of the river. Characteristics according to the Bradshaw model, and there you go with some theory again. The characteristics are that you're going to see much higher discharge, much higher sediment load being transported as well by the river, and that the valley is then flatter around it with a lower gradient. Okay, so that brings us to the end of our section on river channel processes and landforms. So far in 1.1 and 1.2, there's been a huge amount of vocabulary. Definitely answer all the short questions and definitely write out all the main features here. In this course, then, the deltas were in the old course. In the new course, we're not expected to explain deltas. So just in case you see that in textbooks or any old resources, just remember that that's been removed from this updated course. Hi everyone, this is Brian. If you're really enjoying these videos and they're useful, please do like them, leave some positive comments, and make sure you subscribe. By doing that, I can keep making these videos and helping more and more students. Thanks very much. In Unit 1, then 1.3, we're looking at river flood hazards and impacts. In this, our learning objectives, there's three main ones here: to explain the physical and human causes of river flooding and the factors affecting flood vulnerability, assess the social, economic, environmental, and political impacts of flood events, and evaluate strategies used to predict, manage, reduce flood risk using real-world examples. In this case, you need one major case study in this section of the course, so you've got to know one particularly well. You can also use multiple case studies if you want, but know one mainly and be able to just answer essays on one, and then you can also use other ones as other examples. So first we'll go through it without the case study examples, and then I'll go through it with one case study example. Okay, so the physical causes, we've looked at this in Unit 1.1 and a little bit in Unit 1.2. So we're again coming back to this idea of what creates a higher discharge that leads to the level of flooding. So if you haven't looked at 1.1, I'd suggest you go back now and learn everything there. Make sure you're up to date on all your vocabulary worksheets and or your vocabulary sheets and your short question worksheets to this point, and this should be fairly straightforward. However, if you're just jumping into it at this stage, you might find some things maybe a little bit confusing. So make sure you're on the Geography Academy and downloaded all the complementary resources there. Okay, so the physical causes of floods, increased precipitation is the main one. An input into the system can cause the channel storage to increase and then overflow. Snow or ice melt, we mentioned now a few times. This concept that if it all melts suddenly, then it can go into the river all at once. So imagine 3 to 4 months worth of precipitation locked up in the mountains, and then it suddenly comes down all at once over a couple of weeks. We see a huge increase in the discharge, and this can cause flooding. Coastal storm surges are where the waves are so high with tropical storms coming in that they're able to push through the barriers of the coastline and flood the coastal area. Whereas earthquakes and landslides, these can suddenly change. We can see things like these large rocks up here potentially. If we were to see an earthquake crack some weaknesses here and some big rock fall into the water, for example, this would cause the mass to increase and could cause things like mud flows and all sorts of issues there. But it basically caused an increase in the discharge in the river in a short term. So we look at human causes then. We've already checked out what increases surface runoff. So that guide to what increases surface runoff, it's the fastest way water flows into the channel store. And then we're going to see the discharge increasing. So we're always thinking about similar stuff there. Building impermeable surfaces is a big one. So most cities are designed not to hold water, but to get rid of it as fast as possible. It's going to get it off the streets, into the drains. And we see lots of impermeable surfaces. So like in buildings, there shouldn't be leakages with water pouring through the building. So because of that, it means all the water is moving very fast into a channel to push it out of the urban space, and this can create then a high amount of surface runoff and high discharge. Hydroelectric dam failure, for example, dams are used to control water sources and also to control flows. They're also a control to reduce flooding. However, dams have been known to fail, and when they do, the floods are pretty catastrophic. Building on floodplains. In most towns, villages, when they were created, most of them are close to a water source, and most of them aren't in very high, inaccessible places like in mountains. Most people live on floodplains, flat areas of land, great expanses, and large water sources close by. So, this means that just in that essence, they're causing the chances of flooding and the damages and impacts from flooding to increase there. We also think about removing vegetation. So deforestation for something like agriculture, as we can see here on the top right, we talked about this in section 1.1, how suddenly with no interception storage, we're going to have more stress on the soil and for infiltration rates. They can be exceeded. The antecedent moisture then can be very high. This means that not a lot of water can get into the ground. So again, it flows as surface runoff and then it will more rapidly get down to the channel storage. But also you're missing out on something completely because not only is the lack of interception now due to deforestation going to cause that, but it's also going to reduce the amount of water in the vegetation store and it's also going to reduce the amount of evapotranspiration in total. Bridges and other obstacles then block the waterways and cause more flooding. And engineering, believe it or not, if you prevent floods in some areas, you might be causing them further downstream. So let's take a look at a few of those ideas. When we look at irrigation methods, then we can see that it's an issue when we think about the way we're dealing with agricultural land and we're removing forest in that case. But poorly managed irrigation then means that we don't have the right amount of trapping of the water, which means at certain periods then large amounts of water are set out each day. Then they can infiltrate, they can go through flow, they can also pass through groundwater flow as well, or just surface runoff from agricultural areas, and this may lead to a higher amount of water being sent in there. Now, we mentioned deforestation. Here's just a list again, just to go through it step by step, because it's one of the most important ones that students have to write about consistently. We think about deforestation. So we know that interception decreases, infiltration decreases, soil becomes compacted potentially. So we can see like the air water mix on the soil and the natural vegetation, so they can get compacted over time, especially if it dries up quite a bit too. Surface runoff increases, which we've mentioned, and the lag time becomes shorter. Remember your hydrographs from 1.1. Lag time becomes shorter. Peak discharge increases. Flood frequency and magnitude also increase. That's quite an important one as well. We'll talk about frequency and magnitude a little later. Dam failure can happen, as I said. One of the case studies that's coming forward is a more modern one in the course, and most students will have come across it by this stage, is the 2023 Storm Daniel caused the Derna Dam to burst. And when it did so, it also then uh, all the water from the first dam went through to the second dam and broke that as well. So we can see 4,300 people died. We had 40,000 people displaced and huge infrastructural damage done to major cities there. So that was a particularly devastating event in quite recent history. And I know one of the main textbooks for the course uses this as a main case study, so it's a good one to have ready to go in causes of floods. In terms of the bridge, then, the idea is that when you're building a bridge, you may change the channel a little bit, you might decrease the size. So the area at the bridge as the river is trying to pass through is usually the point where, as it's going through, it suddenly hits more friction. There's smaller areas, the river banks or beds then might actually get flooded in this area and move out there. So also if it's carrying like things like wood or trees and they're getting pushed down by the floods, it can create its own barrier in there as well, and it can block up behind the bridge. This can make it very dangerous, like in the 2004 Boscastle flood, where the point and the site of the flood became highly destructive closest to the bridge in the town. Now, when we look at engineering, there's different examples. Now, obviously, the goal is to reduce flooding, but often it's to reduce flooding in an area that has a high population or a high economic value. So this means that they may not be thinking about what's past this point. So here we can see levees, big levees built up. So they look like artificial levees there. You've got a path and then other natural levees and tree lines and vegetation lining this whole river. That's a really good start here. It means that the channel capacity then and its depth is really good, and anything that's over this side of the wall is probably protected. But why would we build a channel so straight? Well, this is likely a canal, which are built for transportation reasons. However, a lot of rivers undergo river straightening, and this is instead of the meander. So the idea of the meander is that the river could, at any stage, maybe flood different sections if you were on either side of the meander, and this may cause multiple flooding points. To straighten the river then, and to make it as straight as possible, this means that the water is going to run fastest. So the water is going to run out of this area as fast as possible as the flood is happening, and therefore it effectively gets rid of the water. But this means further downstream, we're going to find that some areas then will have to take the brunt of that, and you may have to have actually organized floodplains where people are going to be paid to use their land and to be flooded. So that's how these engineering projects can work. We take the danger away from the bigger population and we put it to somewhere else. Now, flood intensifying conditions. So we imagine that the main condition is that it rains too much, the river fills up, and it floods. All of the other ones that we mentioned here, antecedent rainfall, saturated soil, frozen ground, snowmelt, these are all ways in which we're reducing infiltration or we're reducing the input very suddenly. So again, coming back to our idea about snowmelt. Now we look up at the high valleys and bigger mountain ranges like the Himalayas, for example, where some major rivers expand out from, like the Brahmaputra. And in this case, you've got the melting glaciers in the spring, all the snow melt, and this rushing down the valleys from every pocket here. So during that stage, we can see that frozen ground will stop infiltration. The soils will either be frozen or saturated underneath these areas. And we would find that the high snowmelt then suddenly is going to cause a combination of really high discharge. Now, this is coming back to the idea of our braided channels in section 1.2 as well. It's undergoing that similar extreme conditions, especially seasonal change and high input. High drainage basin density that we covered in 1.1, urbanization, deforestation, bridge blockages, river engineerings, we've now mentioned them. So flood intensifying conditions. Climate change is one we haven't come into yet, but as part of that, we can think about some of the extremes. So every climate is going through climate change in a different way. We can't just say that there is overall more precipitation because that's not true. Some places are going through higher levels of drought, for example. So, how do we change this, or how do we bring climate change into this explanation of flood intensification? Well, we've seen things like more extreme years of precipitation. We've also seen extreme periods of drought. So, if we just take precipitation levels into consideration, what we have ended up happening is we have prolonged periods of drought, less vegetation growth. The soil is then has less of a capacity for infiltration. So when it does rain, it can rain in much larger storms very suddenly, and then we could see flash flooding and a inability then for the soils to take in such high amounts of precipitation very suddenly. On the other side, we might see an intensification in snow buildup and snow melt. So snow melt then can be more extreme because of rising temperatures. What we tend to not see is because the average temperatures are increasing, we don't tend to see the rate of ice expansion in the winter increasing. So that's something that is pretty universal around the world, not everywhere, but in many places. And so climate change affecting different places in different ways. So coming back to our table before that you learned in 1.1, you should be very familiar with these concepts of increasing river runoff, decreasing river runoff. If you haven't, go back, maybe download the revision pack or have a look through 1.1 section again and just make sure you're up to scratch on this. You can watch the video again, for example. Okay, flood vulnerability, physical factors then. Vulnerability means, what are the chances of you being hit by like a natural disaster, right? So this vulnerability to the actual hazard. A big difference if you're using any of the resources from last year and this year is this idea of studying this more like a hazardous environment and not just as a flood in a drainage basin. So we're going to have a look at other things. So vulnerability, if you're in low-lying land, that's fair enough. You have more chance to be flooded. Floodplain locations. Steep catchments, what we were looking at before, steep catchments can cause lots of rapid flow with lots of high drainage basin density, tributaries, for example, and this can cause then an increased risk. Impermeable geology, snow melt, tropical storms and monsoons. So this is a tropical storm you can see here. It is absolutely enormous. And as it's coming in and it's hitting the land, it's going to have been raining for days before. So the land is getting the precipitation, quite a high amount of precipitation, which is increasing and increasing every day as this storm is coming across. So as it's about to make landfall, then they've had loads of precipitation and the rivers are all flood up. All of the drainage basin stores are full up and all the rivers are trying to run outwards. While the tropical storm then is coming in with all the high precipitation, it's always creating high amounts of winds. Those high winds then are creating these huge waves that start to move towards the coastline and cause storm surges, which we mentioned before. So you have rivers trying to get out, and you have storm surges trying to push into the coastline, and of course, this leads to huge flooding. Monsoon climates then means that you have an intensity of precipitation at certain times of the year. During that period, then the precipitation levels spike for a very little period and then it goes back down, leaving the rest of your time to a dry season. So, again, we have that extreme that if we don't have consistency in precipitation, we tend to see lots of vegetation dying off, and then the soil at the initial period around here is not going to be able to take or infiltrate all of that precipitation, and this will increase the drainage basin outflow then quite a lot. So the discharge will reach its peak and will be able to hold there for a while, and then we'll see a decrease back into the dry season. So monsoon climates there. Flood vulnerability, then human factors. A couple of ones maybe we haven't mentioned. We have mentioned the idea of river engineering, climate change. Human factors, we put climate change, enhanced climate change. There's a natural and enhanced, and we go into that in different parts of the course. Agriculture, we've mentioned impermeable surfaces, deforestation. Let's have a look at the other side. Building on floodplains and urbanization, we mentioned again, impermeability, but the idea of more people living in cities means that it's difficult to protect these environments that aren't used to naturally getting that. Again, anything that causes deforestation is going to cause a rapid rise in the rising limb, a higher peak discharge than normal, and often a shorter lag time. So that idea then of urbanization will increase deforestation as well. Population density is important because we think about vulnerability. So the vulnerability is there as population density. If it's a high population density, like in Dhaka, in Bangladesh, where you have a high amount of floods, you've got monsoon seasons, you've got the snow melt in the Himalayas, you have huge rivers, and they're all converging in one point. But you also have one of the most densely populated countries in the world, and one of the largest densely populated or cities in the world as well. So this means that they have a high vulnerability at this stage because of their population density, infrastructure concentration as well. So we see urban spaces often in major areas. So mega cities on deltas, for example, are at high risk. So you're always increasing the vulnerability. It's not just the vulnerability that more people will be affected by the floods if the floods happen. It's also, can we help those people too? So it becomes much more difficult to do so under those conditions. The idea of vulnerability, we can bring it into the development level ideas. Now, if this is your first unit in the course, this is good to go through. If you've already been studying human geography, this might be a bit straightforward. But anyways, we have low-income countries and middle-income countries. What do we mean by that? Well, we have this rating system with the World Bank where they will tell you what is an LIC, an MIC, or a HIC, a high-income country. And once the average income then is over that set amount in US dollars, they're considered, low income, middle income, high income. There's a lot of countries in the middle income section and not so many left in the low income section. This is why we kind of talk about them together as well. And because a lot of countries are transitioning from LICs to MICs all the time, and MICs then are made up of lots of different categories. You can actually subdivide MICs into upper and lower MICs too. It's quite a big difference. Now, if you're an LIC or an MIC, there's more chance that you have poorer quality housing, limited forecasting, weak emergency services, poor drainage, limited insurance, and slower recovery. This means that your vulnerability is higher. So if we just take one of those, for example, the idea of limited forecasting. It could be forecasting or also warning. A lot of weather forecasts then are quite universal or international. There's a lot of information shared, and technology is bridging the gap between them. So maybe forecasting is being reduced, but when we think about forecasting, we also need to send information out, especially if there's something like a tropical storm or expected beginning of the monsoon season. In that case, then we can see that limiting forecasting could be limited access to forecasting as well, with things like internet access and communication technology. So there's lots of rural communities in LICs and MICs that might still be vulnerable to that. In HICs, you might see better prediction, stronger flood defenses, insurance, and fast recovery able to deal with it. The flood defenses then are very expensive, and because you have such mixed housing in LICs, MICs, it's not as it may be cheaper to do it in LICs, MICs, but it is relatively quite expensive for their government to produce that. What we see in HICs now is they will have things like insurance, they will have stronger flood defenses, but each time they try to make defenses, the cost is astronomical, and insurances then will only cover so much, so they're kind of limited in what they can offer. Higher economic losses, then way more expensive infrastructure, greater value of assets. So it just means that the potential there for the impacts to be quite high and the stakes to be quite high there. Okay, so that is sort of what's causing it. That's where people have their vulnerability. When we think about, we'll just take a second just to talk about this concept of risk then. So this is something that might help you to think about how we learn about hazards. So actually here it is. The risk equation here equals hazard times vulnerability divided by capacity to cope. The hazard itself is the physical event. In this case, it is the flood. The vulnerability, how susceptible people are to suffering and damage and loss. So we put these two together, the actual hazard, the vulnerability, and this is going to be how large scale the impacts are going to be. And then this can be either made worse by a low capacity to cope, the ability of a community or country to prepare for, respond to, and recover from hazards. That capacity to cope then in some countries can be very high. So we could have a very large flood, which means the hazard increases drastically, and the vulnerability might be relatively low, but the capacity to cope could be very large. And that means that in the end, the actual risk is quite low. On the other side, we could have a relatively low hazard, so a small flood. However, the vulnerability could be very high, which means that we could have densely populated areas in an LIC, for example, and the capacity to cope then is incredibly small as well. So, with a smaller capacity to cope, then, and a large vulnerability, even though the hazard is small, the risk would be considered high. So, think about that and come back to it when you've looked at the case study as well, and think about, well, what was the risk factor before and what was the risk factor then after they had made changes in that case study. Okay, so managing the impacts of floods, then we have hard engineering looking at channel width and height. To increase channel width and height increases the amount of discharge for the river coming through. Flood relief channel and a spillway does the same. We divert water for a period of time into empty channels. This allows a relief for the main discharge in the main channel, and this means that it won't exceed its bankful discharge and flood. Artificial levees, then again, it's very similar to increasing the channel height because you're raising the banks around it. But as we looked at before, those banks can then be really helpful to protect certain properties and infrastructure there too. River straightening, we mentioned already this concept that we can get water out of an area fastest, but then we can also, on the other side, we can see that it might increase flooding downstream. Moving settlements and infrastructure. We need to do risk assessments in these situations and we need to be able to react accordingly. So, moving settles and infrastructure sometimes for hard engineering projects happen as well, and one of those is our final example here, dams and reservoirs. So, dams are built to hold water back, and the reservoirs are the area that fills up behind them. The dams then can open their gates at different times, and this is really advantageous because if there's a flood expected, in a couple of days beforehand, the dams can open up and release some of their water potentially. Then they can close up as the precipitation event happens and they can store the water in the reservoir and they can recharge. When we were talking about a lot of cases about the cause of floods, also of large amounts of discharge in general, we talked about seasonal change. If you go back to your annual hydrograph, for example, as well, you're going to see this example coming through of the snow. So in this case, during the snowmelt period, reservoirs will be prepared to take on huge quantities of water during this time. So they might well let their water levels go quite far down before this period of snowmelt happens, for example. This reduces heavily, all of these can be really effective. The dams in particular can be very effective at reducing the risk of floods and controlling the flow of water. But as we said before, dam failure, and even if the dams get too full, they have to release a lot of water and open a lot of gates. This can increase potentially the flood risk too. Soft engineering, more long-term techniques, afforestation, reseeding vegetation. Getting more and more and more vegetation means we have more infiltration into the soil because we have more intercepted storage. We're going to have more evapotranspiration out of the atmosphere. We're going to allow for more infiltration, which means more soil water store capacity is filled and the groundwater store is also recharged. This means not all the water goes into the river channel and is probably the most effective of the engineering methods in the long term. We can see other things that relate directly to that, like reducing forest fires and overgrazing. We want to keep as much vegetation intact as possible. When you think about it in a real climate, if you just have natural original forest or whatever the types of landscapes might be in the vegetation types in the region, what you'll see is the plants are reacting to the climate. If we were to go back thousands of years before humans developed in so many areas and just focus on where there are forests or where there were forests, you would have seen a very controlled drainage basin system because there's only as much vegetation as precipitation and the temperatures and sunlight will allow for, which means they get into an equilibrium. So anything got to do with going back to that natural environment is going to help reduce the flood risk. Wetlands conservation is one that forms in our case study here as well a little later on. It's quite an important one, so we're going to come back and discuss that in a bit more detail. Here's an example of how agriculture can be changed in order to match the demands of the level of inputs into the system, the precipitation. So we're in more of a tropical environment now. We're in an area where we see monsoon rains. And at that point, that means that's a large amounts of precipitation suddenly. Now, not only do we want to reduce the risk of floods, but we also want to maintain the land and keep soil there and not cause a mad erosion in this area and to utilize this for agriculture. So terrace slopes, as an example, is a really good example actually. So we have got tree lines in order to increase interception, storage, and all of that, stabilize the soil between the terraces. What we see is these artificial walls have been built, or they're called bunds. They are then trapping water and soil and nutrients in these areas, so things like rice can grow in these little rice paddies here. And then you can control the flow. So you can break the bund here and you can allow water to actually come out and go into the next level and so on and so on. And that means as the rain actually stops, then you still have water stored in your bunds as well, and you can continue to use that even after the stronger rains have stopped. So it stops then any major flow of water that's uncontrollable that might cause vertical erosion in places like that. So just an example of how agriculture can cause these risks, but can also be the solution to it. Managing these impacts, then forecast and warning is incredibly important. We have weather radar, rain gauges, river gauges. The weather radar then is showing the precipitation, wind speeds, humidity, those type of things, the amount of sunlight we expect, and evaporation due to that. So that all comes in through the weather, which is important. That's a forecast. Then we have the rain gauge and the river gauge. These are monitoring exactly what's happening. Rain gauge looks at the amount of precipitation hitting, and the river gauge then can be placed to watch the discharge changing in real time then throughout the entire drainage basin. So this is very important then when a flood actually happens, because then people can be evacuated ahead of time. They can also put up short-term defenses as well, which is very important. We talked about hydroelectric dams and how they might work, so now you can actually like close or open your gates according to what you need. So this forecast and warning is incredibly important. But not only that, but all of that data is then going to be used later, where we're going to make long-term forecasts and have a frequency interval for our floods too. So the frequency interval then here we can see we're looking at the reoccurring interval over time. So this allows you to look at the frequency of floods. We can make hazard mapping, we can make defensive changes, we can bring in government budgets, and we can start funding major projects to reduce the risk of floods in those regions, whether it is hard engineering or soft engineering. We look at hazard mapping then as well. This is really important in all our hazardous sections throughout the course. We mentioned this land use planning, keeping people and infrastructure out of high risk. I mean, that's probably the most obvious start. So if you have someone who wants to plan to build on land, there's a high risk of flood. Insurance companies might not cover you. This might end up creating a large problem. So instead of adding value to this land and then having to ask for flood defenses and go through all these different processes, it might be that it's best to deny planning permission on particular sorts of land and to have it as a no build zone because of the frequent flooding. Engineering and flood defense designs, where it's going to go and why is very important. So hazard mapping is bringing us all that information, and it's bringing those engineers to the right places that are needed. Emergency management and evacuation then is something that has to be managed very clearly. You need resources to go in. You might need to evacuate people or casualties. So having access to that and understanding where the emergency services should be going or where the victims should be going is very important too. Public awareness and behavior and change, we see that people have to be trained in order to react to this. In a lot of cases, people will never experience a major flood. And even if they do, it might not be their home and their property that is damaged or their lives that are at risk, even if they experience it. However, in certain areas, hazard mapping can increase our knowledge of the chances of this happening, and it can educate people on how to react against this. Insurance and funding mechanisms, then, to ensure fast recovery is very important in most countries. This is another difference that we mentioned between LICs, MICs, and then the HICs. There's the different levels of insurances and cost that comes with flood prevention management and then rebuilding afterwards and recovery. So this can be helped by hazard mapping and can make the process a lot smoother. So here for impacts, we're looking at the social. This is part of what I usually tell students to look at for causes and impacts of anything in geography, divided into SEEP, and think of that all the time. Will help actually to plan out essays a little later. So you'll hear this again and again in the course. The S stands for social, E is economic, E is environmental, and P is political. So if we're using that, we'll start off with the social impacts. So social impacts then are looking at things like housing. Should put it over on the right one here. So yeah, we're looking at housing destroyed, injuries, missing persons, damages to essential services for people like hospitals, contaminated flood water, waterborne diseases, and looking at community disruption. There's also the long-term psychological impact, stress, anxiety, and post-traumatic stress disorder, PTSD. We look at economic damages then, and that can be to infrastructure. There's going to be a cost to everything. Emergency response is expensive. Having businesses closed for multiple days, having trade interrupted, having food supplies interrupted, having farms destroyed for that season and being unable to produce. This is causing widespread economic havoc along the areas, as well as the insurance claims that we mentioned before. And this is quite important because once they've claimed, it might increase what we call the premium. So this is the upfront price of paying for the insurance versus the cost of what it would cost the company to pay you back in the likely event of a flood. So the less flood defenses they are, the more dangerous it is that you might not get funds to recover that. Okay, looking now at the environmental. So SEE, social, economic. The second E is environmental. We look at riverbank erosion, channel instability, just talking about our systems there. Ecosystems, so all of the aquatic or close to the river ecosystems can be destroyed. You've got breeding grounds, things like beavers, birds, these sort of things living close to the river then and reliant on it can destroy their either their habitats or their food source as well, which is quite important. Pollution of sewage, fuel, chemicals all can run in surface runoff into the river or into the soil and then through the soil as through flow. Large scale erosion transportation can cause sediment. It can alter the channel's shape. It can also reduce the water quality, and this can reduce the aquatic life. If you decrease the oxygen in the river, it's very dangerous for that to happen there. Again, we'll talk about this in another section about eutrophication. So, which you can find on the big vocabulary sheet too. The landslides then potentially that come with it, invasive species and pollutants spread to the environment, and long-term changes to floodplain ecosystems and river morphology, kind of mirroring what we said in the beginning with either destruction of habitats or altering them. The political one, so SEEP, P for political, we see that the governments have to coordinate all the emergency recovery. Now, this could be a national, local, or it can be an international effort depending on the scale. Forecasts and emergency services are often, and their communication levels are often through the government. So they face fierce criticism if they get anything wrong because the stakes are very high. Increased spending on flood defenses often come through the government as well, and being able to repair comes through that point too. And taking on aid internationally can happen as well. So all of these are reliant on political responses. Looking at the potential for positives of impacts as well, this is something that's mentioned in the course curriculum this year, so it's something worth noting. Here we can see natural wetlands. These are areas that have high replenishments of water coming through into it. These areas then are meant to be inundated with high levels of water, and all of the vegetation and the ecosystems built around it rely on that. So definitely places that tend to flood or remain quite waterlogged are then going to rely on that discharge every year potentially for flooding again. We see one of the number one ones over the history of our time. In section 1.2, we talked about this idea of floodplains increasing in size. Well, during that process, we saw all of this, all of these minerals that are coming from the upper the upper course down to the valleys are being broken down through attrition. They finally end up as silt, and all of these minerals that are in the rocky silt is going to be spread out along the soil, and that's going to end up being help the fertility of the soil and for plants to be able to grow. So this is known as alluvium. The aquifer recharge is also very important when we think about the groundwater storage and the water table. So the more we have, then the greater the water table is going to get, and this is going to be very important because we need that to access things like aquifers as our water source. So remember that 22% of our fresh water is locked up there. We see maintenance then of the fish breeding areas too, and floodplain habitats as well, which rely on these regular floods. So it can be useful, and it can certainly be positive in the natural environment. Now we're moving on to the case study. This is where you may or may not find this useful. At the end of this, you might think, oh, well, this is a very good case study. I want to use it. You might think that this is not as good as the one that maybe you picked up in school or you got off some notes online in a different area. And that's absolutely fine. The main thing is that you have one main case study that you're able to answer all the major questions about. So go on to our premium section there, or the exam prep program, in order to get a list of the potential essays that can come up and will likely come up in this new exam paper. But here you may want to use this case study, or it might be a secondary case study. You might have something that's contrasting. There might be something interesting in this case study that wasn't mentioned in the last one. But if you do go and decide to do your own case study, just look through this and see the headings and try to get something that's similar in order to be prepared for planning your essays and executing them at a really high level. It is quite difficult, it's impossible to get full marks without having good relevant case study information, so you want to focus on that. Now, because I'm giving all the information on the slides and I also have the revision notes and everything like that, you just can download those and you can read through them. I'm just going to talk about the general idea of this case study, but the slides have lots of detail on, so you can use them in your exam. A question I get all the time is, how much case study knowledge do I have to know? The answer is across the course quite a lot. It is very important, but it also helps you to plan, which is so crucial. So having the right case study is quite important. Okay, so we're having a look at this Somerset flood. It's 2013, 2014. We see there's multiple rivers coming in, flat land, lots of grazing, agricultural land, and small villages. So it's a large area with multiple smaller settlements that we're discussing here. Physical causes then, we have prolonged precipitation or rainfall, events happening from February to, or December to February between 2013 and 2014. So note that it's not just a single event. So we have records since 1766. 600 millimeters of rain fell in January alone, double the monthly average in parts of Somerset. The rain fell on already saturated ground, resulting in extremely high surface runoff. So we talked about this with antecedent moisture, again going back into our storm hydrographs and the causes of changes there. So we're resulting in huge amounts of river runoff that can't be controlled. It's in the winter as well, so there's less transpiration too and less evaporation. So there's less water leaving the system that way. And because the plants aren't using the water as much during the winter, we find that it's not taking water from the soil. The soil also might be a bit more frozen at times too. So we see that's lying on alluvial clay soils and peat, so these can become saturated quickly, reducing infiltration. Groundwater levels already close to capacity. So low-lying topography, building on a floodplain, and having the funneling effect between different regions. So surrounding higher grounds then just make certain areas then even more prone to that flood. As we can see here, it's expanded out into multiple properties. There's the original river running through there, and we can see how it covers quite an expansive area outside of what it's normally used to. The Bristol Channel with a high tidal range of 15 meters, tidal surges. So this means that where we have our estuary and the water is leaving the system, it's trying to get out, and that's good and can reduce floods, especially towards the lower course where we have our estuary and lots of flat land together. So then the tide is coming up the estuary, and suddenly that's causing a bottleneck at this area and doesn't allow all the water then to leave, causing floods in and around that area too, making it way more dangerous. So we look then at the tidal blockage. A lack of drainage then, so no dredging. So dredging is another type of, I guess it's a hard engineering technique because you are altering the shape of the river channel. So this dredges then means that you're going to take a lot of the silt and sediment that's been deposited at the bottom of the river, and you're going to take that out of the river with like a big digger, and then you can put it onto a boat or something, and you can bring that sediment away to be used as maybe alluvium for agricultural land, for example. Now, this is going to make it deeper and increase the capacity of the river, which is good, but if it's not been done properly for over 20 years, this means your river can hold a lot less than it should. So too much silt build up, the capacity decreases, and no efficient dredging had occurred. Drained wetlands and intensive agriculture. This is quite a unique one for this case study, but it does happen in many places around the world. So what we see is the wetlands we looked at before, they're drained out. We're making channels that take all the water out of the land. So as the water is able to drain out of the land, it's no longer wet land. So the soil left behind is able to be used for something else. For example, for cattle grazing, and sending them into the wetlands, or the old what used to be wetlands in the upper course. And what we're doing is we're reducing the amount of water that's retained in those wetlands, which means it's all flowing down then faster into the channels. So this is quite a dangerous thing to do, to change such a natural environment there. Human causes, then, we can always think about the raised embankments, roads, drainage ditches, all meant to alter natural courses and to send the water out of the area in the quickest time possible. So this is obviously going to lead to more channel storage, water in the channel storage area, and then potentially a flood as well. Delayed maintenance, as is the case with a lot of floods, a lot of the criticism that comes in afterwards was the knowledge that they were in an area, the hazard map that tells them they're in danger. The threat is there, but we're just seeing a delay in maintenance and a priority not being given to these places before a flood. So this is why we often have to deal with the consequences of a natural hazard instead of fully preventing them. The social impacts, then, we mentioned the last time we have social, economic, environmental, and political. What I'm going to do is I'm just going to let you pause here, have a read through, and take out what you think is the most significant. So one thing to note is the environmental agency and the Met Office are the ones that supply the information to the people. Having a good idea about the homes that were destroyed and the people that had to be evacuated and how they did that, like the isolated villages, for example, supported by boats and helicopters by supplies. So that's quite a unique one to this one here. They cost about 15 million. The size of the agricultural land that was submerged then is there as 11,000 hectares. So transport and infrastructure, the railway line then and the roads disrupted, and then access reduced to multiple places. And as expected, the insurance premiums rose for all those people. So their cost of living from now on is going to be much more expensive, even with the repairs and everything done. So the overall estimate then 147 in direct and indirect crosses for our costs from Somerset is very, very high overall. And we can see the environmental impacts then altogether. So things like waders, like the lapwing, redshank, then in decline afterwards. So definitely that's going to have a knock-on effect to the food chains in the area. Earthworm populations dropped, but recovering. But this is just an example. I mean, the worms then act as a good addition to decomposition and also is part of a food web as well. So we know that then there's going to be a reduction in the animals that eat the worms too, as well as overall the soil having negatively impacted then from that. Last there, it says soil degradation occurred due to prolonged waterlogging. Crop cycles disrupted as well into the growing season of 2014. So degradation, the idea that it is reducing in its quality then because of this, taking a long time to recover. The impacts of political was high criticism in the environmental agency and the river authorities as well. So yes, they were under a lot of scrutiny and then they made some big changes. All right, so we're looking at a couple of hard engineering ideas here. Diversion channels was put in for the Soe River and the Sagamore Drain, and this allowed then for the capacity to increase during times of flooding. Pumping stations as well were set up in order to remove the water, so being able to put pumps into certain regions and take them out of a flooded area. The tidal barrier that's going in construction right now, so who knows, it might be finished by the time you're doing the exams. This would be a good one to just have a little research yourself and see how they're getting along. The cost going into 249 million. As we mentioned before, the estimated cost initially was about 147. So if you think about that, then this sort of large, expensive, very technical piece of hard engineering hardware is going to be able to protect thousands of people's homes and thousands of businesses from the combined tidal and fluvial flooding. So, if we looked at that, that is less than the cost of two floods happening again of the same scale. So this is a long-term solution, but when it is completed, it has an immediate reaction. So it's going to be able to do that job straight away. And this makes it incredibly useful. So we're always looking at that evaluation of the soft and hard engineering approach to these things and really weighing up the difference between the two. That's obviously a big part of some of the model questions and answers that are done on the exam section of the course. So we look at that then, reprofiling ditches. So to make sure that it's reducing surface runoff, allowing for more infiltration, and seasonal control of ditches too, encouraging re-wetting of peatlands. And this was a big one for them, for those areas of wetlands then to be flooded again, to take in the not just the flood water, but to be wetlands in general, and allow this to be a region that can be flooded during periods of high precipitation. So this means that all of the channels that were built to actually get the water out and dry out the wetlands were covered up, and mini dams were built, for example. Bringing back the wetland habitat restoration, creating a site of specific scientific interest. In the UK, this just means it's kind of like being created like a natural park where it's going to be protected, and the species within it then monitored very closely. And that means that there won't be any more building on it or changes to it. So this is bringing back the natural system, which is absolutely excellent for the ecosystem. It means then they can also use it for things like ecotourism. It's going to make them more resistant to floods, but overall it is still small scale compared to the whole size of the drainage basin. So it is part of the plan. It isn't the only plan there. Community engagement, so looking at the River Authority and bringing in different agencies for recovery, evacuation warning, and coming up with plans, the Flood Action Group there as well, to manage local priorities. So bottom up resilience planning. This means that it starts with the locals. They can say what they believe is the best thing for them, and then the plans can be put into place on a more national scale for the funding. So with that, then we've got a couple of hard, soft engineering and management ways in which to go. A little evaluation for each. So we could see perhaps like an essay that would come up like, to what extent can floods be sustainably managed? You can see this divided into maybe like 3 paragraphs and discussed like that. Within it, then very specific case study information and plenty of evaluative language. So during the flood, then we see a reaction, warning systems there, and evacuations ahead of time, pumps put into place, and then reaction to it, then having live flood maps, utilizing all the data, and ensuring emergency services were ready to step in when needed. So warning and evacuation, then there were some evacuation. The Army was brought in and the Royal Marines as part of that for both services. And yes, there was communication errors then on whether to stay or leave. So then we saw, after the flood, a lot of the warning and evacuation came down to either that people were already in emergency shelters, or in some cases, the villages that were cut off could then be supplied with whatever goods that they needed at the time. Hazard mapping then was updated after. Of course, this happens quite a lot. And again, this comes back to government control and government responsibility. After the flood there, we can see the very detailed map brought in using LiDAR and satellite data as well to improve the accuracy of the data that was inputted and creating a much stronger system. So this creates then hydraulic modeling, which allows then them to make a good flood interval level and understand where they can make the changes. The flood interval level then again increasing in the exact same way, all that information coming in very suddenly in order to reduce the threats from floods in the future. Now, with all case studies, with all good case studies, if you're going to use this one or someone else, I would suggest that you use a place that's experienced 2 levels of the same amount of precipitation or somewhere close to it. Now, in Somerset in the winter of 2023-24, they had one of the wettest records, and it was started with 29% more rainfall than in February than the average. So wettest record in the region. Multiple storms coming through, same ideas, multiple causes of the flood there. So nearly double the number of homes flooded between May 2023 and January 2024 compared to that of 2014. But the flooding was shorter lived and less severe overall. So we've learned that things did actually change. It reduced the impacts in the areas worst hit in 2014, which is quite important. Some areas that had experienced an extreme flooding did not this time around. So that's your kind of like big evaluation to bring in and very key pieces of case study information. The natural flood management then, stage 0 catchment works. So interventions then with measures such as floodplain reconnection and small scale barriers then is helping to reduce the risk there as well. And now they have a 38% reduction in peak flood flows downstream. So 100 properties in flood prone areas and reducing the risk overall to infrastructure. So overall, we would say that it was successful in reducing the threat of a flood, like mitigating its impacts, reducing its impacts, or reducing the chance of a flood event. Yeah, and we can see the outputs then of the channel storage increasing there. So this sort of brings us to the end of Unit 1, Hydrology, River Processes and Hazards. The next part to go on to after you've learned your vocabulary and you've done all your short questions, you've downloaded your revision notes from the Geography Academy, then it's on to the exam paper question section. So you have to look at your skills, then look at the questions that will come up, make sure you can plan for each eventuality and to be 100% prepared. Hi everyone, this is Brian. If you're really enjoying these videos and they're useful, please do like them, leave some positive comments, and make sure you subscribe. By doing that, I can keep making these videos and helping more and more students. Thanks very much.